Hello there, and welcome to Science for Sleep, where curiosity winds down slowly, ideas wander at an easy pace, and the universe becomes a gentle companion for the night. I'm glad you're here. Tonight we're going to drift towards something that sounds almost too dramatic for a sleepy moment, but don't worry. Even the brightest things in the cosmos have a quiet story to tell when you approach them slowly enough. We're easing our way into the glow of 3C273, the brightest quasar in the universe as seen from Earth, an object so powerful and so distant that the light reaching your eyes has been travelling for billions of years just to arrive in this exact moment. It's a strange thing to think about as you settle in, knowing that something unimaginably far away has been shining long before humans existed, long before Earth had plants or oceans, long before anything familiar even had a chance to begin. And here you are, resting, letting your thoughts soften as we look toward a place that is anything but calm, but somehow still manages to offer a kind of quiet perspective at the end of the day. Before we drift too far, I'd love to know something simple. Where are you listening from tonight, and what time is it in your corner of the world? It's always interesting to imagine all of us scattered across time zones, each arriving at this shared moment in our own ways. For some people, it's the very end of a long day. For others, it might be early morning when everything still feels a little slow and you're not quite awake yet. And for someone else, it could be the middle of the afternoon when you've decided you need a peaceful pause before moving on with whatever comes next. It's a comforting thought that this quiet little journey reaches you no matter where or when you are, all while we talk about something so far away that ordinary clocks feel almost irrelevant. If you find this gentle walk through the cosmos soothing or interesting, or if it helps you unwind and drift into the kind of relaxed state you've been looking for, I'd be grateful if you'd give this a like or consider subscribing. It helps this sleepy corner of science find people who might need the same kind of calm, and honestly, there's something nice about knowing. This cozy curiosity continues to grow, one quiet listener at a time. Now that we're settled, let's ease into the story of 3C273. Not in a rush, not with any big leaps, but step by step, the way you might follow a path at dusk when the air is cooling and you're in no hurry to get anywhere specific. Because this particular object isn't something you want to hurry toward anyway. It's bright. Unbelievably bright. Brighter than an entire galaxy, even though it's just a tiny point of light from our perspective. And yet, despite that incredible energy, the story of how we found it and what it means is surprisingly calm when told slowly. The name 3C273 sounds almost like a filing code for something misplaced in a drawer, but it comes from a catalogue called the Third Cambridge Catalogue of Radio Sources, which astronomers in the mid-20th century used to keep track of objects that emitted strong radio waves. Back then, radio astronomy was still new and full of mysteries. Scientists were picking up signals from parts of the sky that didn't match anything familiar. Some were stars, some were remnants of dying suns, and some were things nobody could identify. 3C273 was one of those puzzles, a source of radio waves that didn't look like a typical star but didn't match anything else either. For years, it just sat on the list as something unusual and a little confusing. Then came a moment that would quietly shift our understanding of the universe. In the early 1960s, astronomer Martin Schmidt used the Palomar Observatory in California to take a closer look. What he saw was a tiny pinpoint of light, something that looked completely ordinary to the eye. But when he examined its spectrum, the pattern of colours and chemical fingerprints that reveal what something is made of, he noticed something odd. The lines didn't match any known element in the right place. They were shifted, moved far from where they should be. At first, it almost seemed like a mistake, but Schmidt realised the pattern wasn't wrong. It was just stretched, shifted by an amount that indicated the object was incredibly far away and moving away from us at incredible speed. This shift, called redshift, is a way of measuring distance in the expanding universe. The more something's light is stretched toward the red end of the spectrum, the farther away it is. And the redshift of 3C273 was enormous, so large that the implication seemed almost unreasonable at first, This little point of light was billions of light years away, but if that were true, then it had to be unbelievably powerful to appear so bright to us. That was the moment when astronomers realized they were not looking at a star. They were looking at something entirely different. An object so luminous it could outshine entire galaxies. A quasar, one of the most energetic objects in the universe, and 3C273 became the first quasar ever positively identified, the opening clue to a whole new understanding of what galaxies could become under the right conditions. As you listen, it might feel strange to think about something so intense and distant while you're lying still, maybe in a bed, on a couch, or somewhere else where you're letting your mind relax. The contrast between your quiet space and the activity inside a quasar is almost comical. Near the centre of 3C273 is a supermassive black hole with a mass hundreds of millions of times greater than our Sun. It sits in the core of a galaxy so far away that even its shape is difficult to see. Gas and dust swirl into that black hole at incredible speeds, heating to unimaginable temperatures, producing more light and energy than anything your eyes could ever handle directly. And yet, from here, from Earth, all of that chaos reduces down to one small point, something gentle, almost peaceful once you step back far enough. That's the strange comfort of astronomy. The universe can be violent and extreme, but distance softens everything. It gives you perspective. It lets you observe without being overwhelmed. There's something soothing in knowing the cosmos is doing all kinds of intense things while you sit quietly, allowing your breath to slow down. You can think about jets of plasma stretching across entire light years, or swirling disks of matter spinning faster than anything on Earth, or black holes that reshape the space around them and still feel perfectly calm. The universe doesn't demand anything from you while you look at it. It just continues on, indifferent and patient, letting you take in whatever you're ready for. As we continue, the story of 3C273 will unfold in ways that build on each other gently. We'll explore how quasars fit into the life cycle of galaxies, how black holes can power so much light without ever releasing anything themselves, how astronomers use distant objects like this to understand the early universe, and how seeing something so far away is like looking backward through time. Each step connects naturally to the next, not as separate pieces but as parts of a single, continuous exploration. We won't rush. There's no need. The light from 3C273 took nearly 2 billion years to arrive here. It can spare a few moments more while we ease our way through its story. And so, as your breathing settles and your thoughts slow down, we'll move forward. Not abruptly, not with any sudden change, but with the same steady curiosity that got astronomers to look up at that tiny point of light decades ago and wonder what it really was. What they found reshaped our understanding of the universe, and by the time we're done drifting through its story, it might reshape your sense of scale and distance just a little too, not in a dramatic way, but in that quiet, gentle way that helps your mind relax into something larger than the day you just lived. When you follow the story of an object like 3C273 a little further, something interesting starts to happen. The more you learn about it, the less it feels like a simple point of light, and the more it becomes a kind of marker in the vast landscape of the universe. It sits so far from us, and yet its brightness makes it almost feel close, like a distant flicker that somehow reaches past everything between here and there. It ends up becoming a reference point, not just in terms of distance or energy, but in the way it quietly nudged scientists toward a deeper understanding of what the universe was really capable of. And the funny thing is, it didn't do this by standing out, obviously. It did it by looking normal enough to make astronomers doubt what they were seeing. Before quasars were understood, astronomy had a kind of comfortable framework. Stars had specific brightness levels, galaxies had recognizable shapes and behaviors, and nebulae followed certain patterns. There were exceptions and oddities, of course, but most of the sky followed rules that made sense. Then along came objects like 3C273 that followed none of those expectations. From a distance, it looked like a star. That was what the first observers thought, and no one had any reason to challenge that assumption. It didn't appear fuzzy or spread out like a galaxy. It didn't look like a cloud of gas or the remnant of an exploded star. It was a dot. Tiny, compact, deceptively simple. You wouldn't have guessed that it was one of the most powerful things ever observed. But behind that small point of light was something far more extreme than anything familiar. It's strange how often science works that way. Some of the most dramatic discoveries begin with something that doesn't seem dramatic at all. A tiny shift in a measurement, a flicker on a chart, a dot that doesn't behave quite like a dot should, and then someone looks more closely, not because they expect something extraordinary, but because curiosity nudges them. That was the case with 3C273. It wasn't discovered with fanfare. It was uncovered with patient, careful attention to details that didn't line up neatly. The moment astronomers realized this faint-looking point was producing more light than an entire galaxy, everything changed. Suddenly the sky was full of new possibilities. If one quiet-looking object could hide so much energy, then how many others might be doing the same? How many things had been dismissed as ordinary because no one had thought to question them? That shift in perspective is part of why 3C273 feels like a beacon. Not because it literally guides anyone the way a lighthouse would, but because it illuminated a limitation in our understanding. It showed that the universe contained categories we hadn't yet named. For a long time, the idea that a galaxy could produce so much energy seemed almost outlandish. Galaxies were enormous, yes, but their brightness came from billions of stars working together. The thought that a single region within one galaxy could outshine all of its stars combined sounded questionable at best. And yet, that was precisely what quasars were doing. A single compact core could emit more light than everything around it. It forced astronomers to rethink what galaxies could become under certain conditions. As you listen, try to picture the scale involved, not in a grand way, but in a simple, grounded way. Imagine an entire galaxy, something so large it contains hundreds of billions of stars. Imagine every star you've ever heard about, everyone you've ever seen, and everyone you haven't. Then imagine all of that combined light being matched or exceeded by a region smaller than the orbit of a few planets around our Sun. It feels impossible. But that's what 3C273 represents. It's helpful to remember that when scientists first came across this object, they didn't have modern instruments. They didn't have digital detectors, space telescopes, advanced computers, or decades of accumulated research on quasars. They had photographic plates, prisms, and patience. A discovery like this wasn't the sudden result of high-tech equipment. It was the result of looking carefully at something that didn't fit and refusing to ignore it. This attention to the unexpected has always been at the heart of scientific progress. And in the case of 3C273, it wasn't just the brightness that drew attention, it was the distance. The realization that this object was billions of light years away meant that the universe was far more active and diverse in its early stages than anyone had suspected. If something this powerful existed so far back in time, then the early universe must have been a place full of extreme conditions. That idea helped reshape cosmology, adding pressure to existing theories and opening the door for new ones. It's interesting how a single object can do that, how one discovery can push an entire field in a new direction. Not through force, but through clarity. A small point of light saying, in its own way, look again. That's why 3C273 is often described as a cornerstone in the understanding of quasars. It was the first to clearly reveal what they were. It put a name to something that had been puzzling astronomers for years. At the same time, it wasn't isolated. Once astronomers knew what to look for, they began finding more quasars in the sky. Some were even brighter. Some were farther away. Some had stranger properties. The catalogue grew quickly. But 3C273 remained important because it was the one that made everything else click. It showed that these bright points weren't stars at all. They were something much larger and much more powerful, connected to galaxies in ways no one had considered. That's part of what makes it a beacon, not because it stands alone, but because it marks a turning point. And even now, after decades of studying quasars, astronomers still look at 3C273 with a kind of respect. It's familiar, it's reliable, it's bright enough to observe with surprisingly modest equipment. Students look at it, amateur astronomers look at it, professionals look at it, and every time it sits there steadily shining across time, a reminder of a moment when the universe revealed something new. When you think about it like that, the distance becomes even more impressive. The light reaching us from 3C273 started its journey roughly 2 billion years ago. Back then, Earth was a completely different place. There were no humans, there were no mammals, there weren't even dinosaurs yet. Life was still simple, mostly small cells drifting in ancient oceans. Everything familiar to us now was still in the distant future. And through all that time, as continents shifted, climates changed, species appeared and vanished, civilizations rose and fell, that light kept travelling, quietly, steadily, without hesitation. When you look at it through a telescope, you're not just seeing an object. You're seeing a moment that happened before anything you know existed. You're seeing a message that took longer to arrive than entire branches of life have existed. And that alone gives it a kind of quiet significance. It's not loud, it's not dramatic, it's just steady. And in that steadiness there's something grounding. This sense of long travel is part of why astronomy feels so different from other sciences. You're never really looking at the present, you're always looking at the past. The farther away something is, the deeper into the past you're seeing. With 3C273, you're looking back far enough that the human experience becomes almost irrelevant. It's like stepping out of a small room full of familiar sounds into a huge open space where everything slows down and expands. There's something calming in that shift. It's not about feeling small or insignificant. It's more about recognizing that you're part of something long-lasting and stable. Your day might have had ups and downs. You might be tired or restless or distracted as you listen. But out there, far beyond anything in your daily life, there's a point of light that has been shining steadily for longer than you can easily imagine. It doesn't rush. It doesn't change quickly. It doesn't demand anything. It just exists. As astronomers began to understand more about quasars, they realized that 3C273 wasn't just bright. It was structured. It had features that could be studied in detail. It had a visible jet, a stream of energized particles shooting out at high speed for thousands of light years. It had variations in brightness that offered clues about its inner workings. It had a host galaxy around it, faint but visible with the right methods. All of these details helped build the first clear picture of what powered quasars. The heart of that picture was a supermassive black hole, not a mysterious or magical thing, but a predictable, powerful object whose gravity can accelerate matter to incredible energies. As gas falls toward a black hole, it doesn't fall straight in. It forms a disk, swirling and heating until it emits enormous amounts of radiation. When enough gas builds up, processes near the center can launch jets outward at speeds close to the speed of light. None of this was known when 3C273 was first studied, but it helped guide scientists toward these ideas. By looking at how bright it was, how far away it was, how its light changed over time, and what structures surrounded it, astronomers could piece together the puzzle. And as they did, the understanding of galaxies expanded. Instead of being just collections of stars, galaxies became dynamic systems with active centers capable of dramatic behavior. This changed how astronomers saw the universe. It meant that galaxies were not all quiet or stable. Some went through phases of activity. Some lit up with enormous energy. Some evolved in ways that were far more complex than previously thought. The universe became less predictable in one sense, but more interesting in another. And 3C273 remained a reference point in that growing understanding. Now, as you listen and let these ideas drift through your mind, you might notice that the story continues to widen. It started with a tiny point of light. It expanded into the idea of a quasar. It moved into the structure of galaxies, and it's still going. That's how astronomy often works. You begin with something small and end up somewhere much larger, without forcing the journey. It unfolds naturally as curiosity carries you along. The more you sit with the idea of a quasar like 3C273, the more it becomes something familiar. Not simple, but approachable. Even though its energy is immense, its presence in your thoughts can be gentle. That's the contrast that makes it such an interesting thing to explore at a slow pace. Its brightness doesn't overwhelm you when you think about it this way. It becomes a steady point that you return to, just as astronomers have returned to it repeatedly over the years. When astronomers first came across the object we now call 3C273, they didn't realise they were standing at the edge of anything unusual. It didn't call attention to itself. It didn't send out warnings. It didn't behave in any way that would make the average observer pause. To them, it looked like a star. A bright one, yes, but stars come in a wide range of brightness levels, and nothing about this one immediately hinted that it was anything other than another point of light in the sky. That was part of the puzzle. The most powerful known object in the distant universe hid behind an appearance so ordinary that it nearly went unnoticed. If you imagine being one of those early astronomers, you can picture the situation clearly. You have a list of radio sources, objects detected not by visible light, but by the signals they send out at radio wavelengths. Some of these sources match known stars or galaxies, others do not. Among them is one labelled 3C273, an entry that carries no drama. It's just a coordinate, just a point on a catalogue page. When you look at the same location through an optical telescope, you see a pinpoint, bright and crisp. It doesn't look like a galaxy. It doesn't look like a faint smudge. It certainly doesn't resemble anything unusual. If anything, it looks too tidy. At first, this wasn't alarming or confusing. Radio astronomy was still developing as a field, and many of the early observations produced matches that didn't perfectly align with expectations. The sky at radio wavelengths doesn't always resemble the sky in visible light. Some objects stand out in one range and vanish in another. So when astronomers saw that this bright radio source lined up with something that looked like a star, they simply noted it. Nothing more. There were bigger mysteries on the list. There were objects that showed no visible counterpart whatsoever, objects far stranger on the surface. Comparing those, 3C273 seemed almost dull. But the interesting part of science often appears in places that don't look interesting at first glance. It's easy to focus on things that seem unusual, but the real breakthroughs happen when someone starts asking questions about something that looks too familiar. And that's where this story really begins. The turning point wasn't a sudden discovery or a dramatic moment. It came from a simple realization. Something wasn't lining up correctly with the spectrum of 3C273. Taking the spectrum of a star is usually straightforward. You spread its light out into its component wavelengths and look for known lines, the signatures of elements like hydrogen and helium. These lines appear in predictable places. They tell you the temperature, the movement, and sometimes the age of the object. When astronomers looked at the spectrum of this supposed star, they expected it to make sense, but the lines didn't match. They weren't where they should have been. At first, this was confusing. It looked like the object had elements that didn't exist, or that the elements it did have were behaving unpredictably. Both possibilities were unlikely. That left the question of whether the lines were shifted. Redshift was not a new concept at the time. Scientists already knew that distant galaxies had their light shifted toward the red end of the spectrum because the universe is expanding. The farther away a galaxy is, the more its light is stretched as it travels toward us. But this object didn't look like a galaxy. It looked like a single star. Stars are not expected to have enormous redshifts, so the idea was not immediately obvious. This is where Martin Schmidt enters the story again. He was the one who took the time to re-examine the data carefully. He didn't dismiss the strange spectrum. He didn't assume it was a question of misidentification. Instead, he considered the possibility that the object was not nearby. And when he compared the spectral lines to the known hydrogen pattern shifted by a very large amount, everything snapped into place. The lines matched perfectly once you accounted for the shift. Suddenly, the entire picture changed. The object wasn't a star at all. It was far beyond the Milky Way, so far that its redshift placed it billions of light years away. It was sending out more energy than any star ever could. And that meant it belonged to an entirely new category. This realization didn't come with immediate celebration. It came with a quiet sense of disbelief. If the object was that distant, its brightness was staggering. No known object should have been capable of shining that intensely. But the numbers were unavoidable. The spectrum didn't lie. This moment is now considered a landmark in astrophysics, but at the time it must have felt more like solving a persistent puzzle. The strange lines finally made sense. The mismatched data finally aligned. Yet the implications were so large that they took time to sink in. An object billions of light years away that looked like a star but outshone an entire galaxy was not something that fit into existing knowledge. The universe had just revealed something unexpected, and astronomers were suddenly faced with a mystery far larger than they had anticipated. This stage of uncertainty is important to remember, because it shows how much patience and openness are required in scientific discovery. There wasn't a clear category waiting for the object to fit into, no prepared definition, no slot in the cosmic filing cabinet. It forced the creation of a new class of objects, one that eventually became known as quasars, and even the name reflected the uncertainty. Quasi-stellar objects, things that looked like stars but clearly were not. As soon as the concept was recognized, other puzzling objects began falling into place. There were several other radio sources with spectra that didn't match expectations. Once astronomers applied the same reasoning, they realized these too were extremely distant and extremely bright. A whole population of them existed across the sky, hidden in plain sight. They had been recorded in multiple catalogues. They had been photographed. They had been measured. But their true nature remained hidden until someone realized they were not stars at all. That shift in understanding helped reshape astronomy in a slow but steady way. It expanded the known range of what galaxies were capable of. It introduced the idea that the centers of some galaxies could be active, producing enormous amounts of radiation. It suggested that the early universe, when these quasars were more common, was a place of intense activity, and it pushed scientists to ask what mechanism could generate such power. At that time, the idea of supermassive black holes at the centers of galaxies was still speculative. Some astronomers considered it unlikely. Others were unsure whether black holes could grow to such enormous sizes. But as the data from quasars accumulated, the evidence pointed consistently towards something massively compact. A region so dense and energetic that it could produce the radiation observed. Eventually the idea became widely accepted because no other explanation fit the observations as well. When you reflect on the early years of studying 3C273, you can almost imagine how gradually the picture changed. There was no single moment when the entire scientific community shifted its view. Instead, there were slow adjustments, more observations, more spectra, better images. Doubts gradually faded as the data piled up, and through all of this, the object remained visually unimpressive. A tiny dot of light. Nothing about its appearance suggested its significance. That's one of the quiet lessons embedded in this story. Something that looks simple or ordinary can turn out to be extraordinary when examined closely. The labels we place on things are only as accurate as the information we have, and sometimes the universe surprises us not by showing us something new, but by revealing that something familiar was misunderstood. In those earlier decades, astronomers didn't have access to the technology available now. Observations required long exposures, measurements were done manually, equipment was less sensitive. Even so, the conclusions drawn from those early studies remain valid today. Modern telescopes have confirmed them in greater detail, but the basic understanding hasn't changed. That's a testament to how solid the reasoning was, even with limited tools. Over time, 3C273 became not just an unusual object, but a kind of benchmark. It was bright enough to study thoroughly. It was distant enough to illustrate the nature of quasars, and it was stable enough that repeated observations could track changes over time without losing clarity. Researchers used it to refine methods for measuring distances. They used it to test models of galactic centers. They used it to compare with other quasars to identify patterns. In a way, it became one of the first guideposts in the study of the distant universe, a reference that could anchor newer discoveries, providing a point of comparison. When other objects appeared with similar properties, astronomers could say, "This behaves like 3C273, which helped categorize them." And as the number of known quasars grew, the classification became more refined. Some had stronger radio emissions, some had different spectral signatures, some varied more dramatically. But the basic framework remained. The simplicity of how the object looked and the complexity of what it truly was created a contrast that many astronomers found fascinating. It reminded them that the universe doesn't always match expectations. It also encouraged more careful examination of other so-called stars that might not actually be stars. And indeed, several turned out to be distant quasars or compact galaxies. Even in the public imagination, quasars eventually became symbols of extreme cosmic power. But before that, they were just curiosities, entries on radio maps, data points. That slow transition from curiosity to cornerstone shows how discovery often unfolds gradually, supported by patience rather than spectacle. If you were to imagine yourself at one of those old observatories, peering through a telescope or looking at a photographic plate, you might find it surprising that something so faint-looking could change our understanding of the entire universe. And yet, that's exactly what happened. A bright dot revealed the existence of a whole class of extreme objects. A misidentified star turned into something entirely new. And all of this came from quietly noticing that the spectrum didn't behave the way it should. Once astronomers understood that this object was not a star, the obvious next question became, if it wasn't a star, then what was it? Once astronomers accepted the idea that 3C273 was not a star, the next step was understanding what it truly represented. It wasn't enough to label it as distant or bright. The question became more focused. If it wasn't a star and it wasn't a typical galaxy, and it wasn't a simple radio source, then it needed a broader explanation. Something that could include its brightness, its distance, its extreme energy, and its compact appearance. That search led directly into the idea that the centers of some galaxies are not quiet or uniform but extremely active. Before quasars were recognized for what they were, galaxies were generally viewed as stable structures. They had arms, clusters of stars, clouds of gas, and the kinds of features you might expect when billions of stars share the same space. Some galaxies were more irregular, some had brighter centers, some had unusual shapes. But the core assumption was that galaxies were collections of stars behaving more or less as expected. Even when astronomers noticed strong radio sources associated with certain galaxies, the idea of an intensely active core wasn't yet mainstream. Once 3C273 and other quasars entered the picture, everything had to be reconsidered. The brightness of these objects didn't come from stars. It came from something concentrated in the center of a galaxy-sized structure. That alone required questioning older assumptions. Stars, even the most massive ones, could not produce that kind of energy. Supernovae couldn't explain it either. Nothing familiar produced that output continuously. Whatever drove quasars had to be both extremely powerful and extremely compact. The earliest attempts to explain quasars range from cautious to speculative. Some astronomers wondered whether quasars might be exotic types of stars, but this didn't hold up. Others proposed massive explosions or collisions on unimaginable scales, but these didn't match the observations either. The brightness of quasars stayed consistent over long periods, or varied in ways that didn't line up with catastrophic events. Gradually, the idea formed that quasars might sit inside galaxies, not as stars, but as something fundamentally different. The term active galaxy began gaining traction to describe galaxies with unusually energetic centers. This was not an entirely new concept. A few galaxies had been studied in earlier decades that showed signs of activity. Their cores were unusually bright. They emitted strong radio waves. They behaved differently from ordinary galaxies. These were known as Seyfert galaxies, and they had puzzled astronomers long before quasars appeared in catalogues. They suggested that galactic centers might not always be passive, but even then, the scale of activity in those galaxies didn't match what quasars were doing. When quasars were linked to the idea of active galactic nuclei, it became clear that they represented the extreme end of this category. They were not just active. They were overwhelmingly active. They were the most luminous type of active galaxy. Instead of being bright cores within visible galaxies, they were so bright that their host galaxies were overshadowed. In many cases, the galaxies themselves were nearly impossible to see because the quasar at the center dominated everything around it. This realization helped unify several confusing observations. Some galaxies with bright cores, some with strong radio emissions, and some with unusual spectra all belonged to the same general family of phenomena. They differed mainly in intensity and orientation, but the underlying mechanism could be the same. Even though researchers didn't yet know precisely how these active cores worked, they understood that something powerful was happening in the centers of galaxies. The idea of a calm, stable galactic nucleus began to fade. To understand why these active centers were so puzzling, it helps to picture what a typical galaxy looks like in contrast. A normal galaxy has a lot of stars, gas, dust, and dark matter distributed across an immense volume of space. Its core might be brighter because stars tend to be more densely packed there, but the brightness is still moderate. Starlight dominates most wavelengths. There are no obvious signs of violent processes. The galaxy rotates steadily, evolves slowly, and maintains its shape over long time scales. Active galaxies behave differently. Their cores emit far more energy than expected. The light comes not only from stars but from processes unrelated to conventional starlight. Some active galaxies release jets of particles that stretch across thousands of light years. Others vary in brightness rapidly compared to their size. These features don't align with the behavior of normal stars. They require something more concentrated. As scientists continued gathering data on quasars, they noticed that their brightness could change on relatively short timescales. Sometimes hours, sometimes days. That meant the region producing the light had to be small. The smaller the region, the faster it can vary. An object the size of a galaxy cannot change brightness in a matter of hours, but something small, compact, and energetic could. This observation was one of the strongest clues that quasars were not large, diffuse sources. They were compact powerhouses at the very center of galaxies. By this point, the idea of black holes had been around for decades, but they were still largely theoretical. The concept of a black hole with millions or billions of solar masses was not widely accepted. Many scientists found the idea uncomfortable because it implied a scale of gravity and density that seemed almost impossible. But as more data came in, black holes increasingly appeared to be the only explanation that matched all the features of active galactic nuclei. A supermassive black hole surrounded by a rapidly rotating disk of gas could produce enormous amounts of energy through friction, heat, and the conversion of gravitational potential energy into radiation. This process could release more energy than any star or any cluster of stars, and unlike stars which burn steadily, an accretion disk could vary in brightness depending on how much gas was being pulled in at any given time. This matched the observations perfectly. At first, this explanation felt almost too dramatic. A black hole at large sounded like something from speculation rather than observation. But as more quasars were identified, similarities in their behavior strengthened the case. The energy levels, The variation patterns, the radio emissions, and the compactness all pointed toward the same mechanism. Eventually, the scientific community accepted the idea of supermassive black holes as the engines of active galaxies, not because it was convenient, but because nothing else fit. The strange idea that galaxies could be active, not just collections of stars drifting quietly through space, reshaped how astronomers viewed the universe. Instead of seeing galaxies as calm island universes, they began to see them as dynamic environments with life cycles and phases of intensity. Some galaxies were quiet, some were moderately active, some, like those hosting quasars, were extremely active. In this new framework, 3C273 became an important example of the most extreme type. It served as evidence that galaxies in the early universe could experience phases of dramatic energy output. It indicated that supermassive black holes existed long before the universe had matured into the calmer cosmic structure we see today. It showed that these active phases were not rare accidents, but part of the universe's natural progression. Understanding active galaxies also helped answer another long-standing question. If quasars were so bright and so common in the distant universe, why weren't they more common nearby? The answer came slowly but clearly. Quasars were more prevalent when the universe was younger. In its earlier stages, galaxies had more gas and more material available to feed their central black holes. Over time, much of that material was used up or stabilized. Galaxies aged. Their black holes became less active. The universe quieted down. This perspective explained the distribution of quasars. They appear most frequently at great distances, which means they existed during earlier cosmic epochs. Nearby galaxies still have active nuclei occasionally, but not at quasar levels. The activity today is more subdued. The universe has matured into a phase where extreme events are less common. As researchers refined their models of active galaxies, they also learned to predict certain behaviors. If a galaxy had a bright central source and produced strong radio waves, it might have a jet. If it varied rapidly in brightness, the central engine was compact. If it showed extremely broad spectral lines, the gas near its center was moving at high speeds under strong gravitational influence. All of these features helped build a clearer understanding of what was happening inside. When you connect these ideas back to 3C273, its role becomes even clearer. It wasn't just the first quasar identified, it was one of the clearest examples of an active galaxy operating at full intensity. Its brightness made it easy to study, its spectrum made it unmistakable, its behavior matched predictions of what a supermassive black hole surrounded by an accretion disk should produce. It became a reference point not by coincidence, but by its suitability for repeated observation. Even as technology advanced and astronomers gained access to space telescopes and more sensitive instruments, 3C273 continued to play a central role. Its brightness allowed detailed measurements across different wavelengths: radio, infrared, visible, ultraviolet, and even X-rays. Each range of light revealed more about its structure and the processes near its core. In many ways, it became a standard object used to calibrate instruments or test new methods. Through all this research, the idea of an active galaxy has become mainstream. It's now understood that many galaxies go through active phases at some point in their history. Some remain active for millions of years, others flare up and then settle down. Then, the level of activity depends on the availability of material near the galactic center and the history of interactions with other galaxies. Collisions, mergers, and close encounters can feed central black holes and trigger new periods of activity. This understanding also helped explain the diversity of galaxies observed today. Some have quiet, faint nuclei, others have bright centers but are not classified as quasars, some have jets, some do not. All of these differences reflect the stage of activity and the angle from which we observe them. A quasar seen from the side might appear as a different type of active galaxy. A quasar whose jet points toward us might appear even brighter because of relativistic effects. The entire category of active galaxies is now recognized as a collection of related phenomena, not separate mysteries. When you place 3C273 in this broader picture, it becomes less of an isolated curiosity and more of a key example of a larger pattern. But it still holds a special place because it was the first clear case that forced astronomers to accept these ideas. It stands at a turning point in the history of astrophysics, marking the shift from a universe of mostly calm galaxies to a universe full of dynamic, powerful, and evolving structures. As astronomers became more familiar with the idea that quasars were powered by something active at the centres of galaxies, the next logical step was to understand what was actually happening inside those distant cores. It wasn't enough to know that they were bright or far away. It wasn't enough to accept that they matched the behaviour of active galactic nuclei. Scientists wanted to know what the central engine looked like, how it operated, and why it could produce so much energy. This required looking inward, not physically, but through careful observation and analysis, and piecing together the structure from the effects it produced. The challenge began with the simple fact that the core of a quasar cannot be seen directly. Even with the most powerful telescopes, the region is too small and too distant. Instead of images, astronomers rely on the light and radiation emitted from the region around the central source. The patterns within that light carry the information needed to build a model of what lies at the centre. This process resembles listening to the hum of a machine behind a wall and trying to determine what kind of engine is running based on the sound and the vibration patterns. It requires careful measurement, patience, and a willingness to revise assumptions as new data emerges. For quasars like 3C273, the first clues came from the way their brightness changed over time. Variability in brightness is one of the strongest indicators of a compact source. A large object, such as a galaxy-sized region, cannot change brightness quickly because different parts would respond at different rates. For light to vary significantly within hours or days, the emitting region must be small enough for those changes to occur across its entire structure at once. In the case of 3C273, the variations were rapid enough to show that the engine was confined to a region no larger than the solar system, despite producing more energy than an entire galaxy. This realization alone pointed towards something extreme. To produce that much energy in such a small space required a mechanism far more efficient than nuclear fusion, the process that powers stars. Fusion is powerful, but it is not capable of producing the output observed from quasars. There had to be another method, something that could convert matter into energy with far greater efficiency. The leading candidate, which eventually became the accepted explanation, was accretion. When matter falls toward a massive object, it gains speed and energy. If the massive object is dense enough, the energy released can be enormous. Around a supermassive black hole, matter spirals inward, forming a disk. This accretion disk becomes extremely hot due to friction and turbulence. The energy released from the disk can exceed anything possible through fusion. This process can convert a significant fraction of the matter's mass into radiation. A supermassive black hole fed by an abundant supply of gas and dust can therefore power the intense luminosity of a quasar. Astronomers didn't reach this conclusion immediately. It took years of comparing models, testing predictions, and checking them against observations. But as the evidence accumulated, the accretion disk model became the most convincing explanation. It accounted for the high luminosity, the variability, the broad spectral lines, and the presence of jets. It also made sense in the context of gravity and the known behaviour of matter under extreme conditions. One of the most informative aspects of quasars is their spectra. When the light from a quasar is spread out into its component wavelengths, the resulting spectrum reveals important details about the gas around the central engine. In many quasars, including 3C273, the spectral lines are broadened. This broadening occurs because the gas is moving at high speeds, sometimes thousands of kilometers per second. Such velocities are only possible in regions dominated by strong gravitational forces. The broad lines indicate that the gas is orbiting very close to the central object, further supporting the idea of a massive, compact source. The gas in an accretion disk doesn't move uniformly. The inner regions orbit faster than the outer regions. This creates shear forces that generate heat. As material spirals inward, it becomes hotter and more energetic until it emits large amounts of radiation across multiple wavelengths. Quasars like 3C273 emit strongly in radio, optical, ultraviolet, and X-ray wavelengths, each corresponding to different parts of the accretion disk and the surrounding structures. In addition to the disk, many quasars feature large jets that extend outward from the central region. These jets consist of particles accelerated to nearly the speed of light, travelling along narrow pathways that stretch across enormous distances. The presence of jets indicates strong magnetic fields near the central engine. Although the exact mechanism that launches these jets remains an active area of research, the leading theory suggests that magnetic fields twisted by the rotation of the accretion disk can channel some of the inflowing energy into collimated beams. These beams then travel away from the black hole along its rotational axis. 3C273 has one of the most well-studied jets in astronomy. It is visible even in optical light, which is unusual for a quasar jet. Most jets are easier to detect in radio wavelengths, but the one associated with 3C273 is bright enough to be seen with ground-based telescopes in the visible spectrum. This feature provides valuable information about the processes inside the jet, the speed of the particles, and the interactions between the jet and the surrounding medium. Studying the jet also helped confirm the presence of a supermassive black hole at the core. Jets require a powerful central engine with a strong gravitational pull and a rotating disk. The alignment of the jet and the structure of its emissions match the predictions of models involving a black hole with a significant spin. A rotating black hole, surrounded by an accretion disk, can drive the magnetic processes needed to launch jets. This model fits the observations of 3C273 well. Another clue came from the polarization of the light emitted by the quasar. Light waves can be polarized if they pass through certain types of magnetic fields or scattering environments. When astronomers measured the polarization of light from 3C273, they found signatures consistent with synchrotron radiation, a type of emission produced by charged particles spiraling around magnetic field lines. This supported the idea that the jet contained relativistic particles interacting with magnetic fields. It also confirmed that much of the emission from the quasar came from regions dominated by energetic processes rather than from stars. By combining all of these observations, astronomers created a detailed picture of the central engine. At the centre lies a supermassive black hole, likely hundreds of millions of times the mass of the Sun. Surrounding the black hole is an accretion disk made of gas and dust spiralling inward. This disk becomes hotter toward its centre, emitting increasingly energetic radiation. Above and below the disk, magnetic fields twist and accelerate particles into jets that extend for thousands of light years. Farther out, gas clouds illuminated by the intense radiation create spectral lines with distinctive shapes and widths. None of this structure can be seen directly, yet the consistency of the data makes the model reliable. Every observation fits somewhere into the picture. The variability corresponds to the size of the disk. The broad lines correspond to the speeds near the black hole. The jet corresponds to magnetic activity along the axis of rotation. The multi-wavelength emissions correspond to different layers of the structure. It's a complex engine, but one that operates according to understandable physical principles. The idea of peering into such a distant and energetic system might feel daunting, but when broken down into these components, it becomes manageable. Each layer serves a purpose. Each layer reveals something specific, and together they form a coherent explanation for what powers quasars like 3C273. Another important aspect is how this engine evolves. Quasars are not permanent fixtures. They represent a phase in a galaxy's life. When a galaxy has an abundant supply of gas near its centre, the black hole can feed actively, creating an accretion disk and powering the engine. Over time, however, the supply may diminish. The gas can be consumed, dispersed, or stabilized. As the fuel decreases, the brightness of the quasar fades. Eventually, the galaxy transitions into a quieter state. Its black hole still exists, but it no longer produces the extreme energy output seen during its active phase. This evolution explains why quasars are more common in the distant universe than in the nearby one. When the universe was younger, galaxies were more gas-rich. Collisions between galaxies were more frequent. Interactions were more common. These events often triggered flows of gas toward galactic centers, feeding the black holes and igniting quasar activity. As the universe aged, galaxies matured and stabilized. Gas became less abundant near their centers. The conditions needed to power quasars became less frequent. Understanding this evolutionary process provides another way of viewing 3C273. It is not just a bright object. It is a snapshot of a galaxy undergoing a phase of intensity. That phase might last millions of years, but it is still temporary in the grand scale of cosmic history. Observing 3C273 allows astronomers to study a moment that most galaxies, including our own, may have experienced at some point in their past. When you think about it this way, the quasar becomes less of an outlier and more of a natural stage in galactic development. The only reason it appears unusual is because the conditions needed to sustain such activity are not common today. In its own time, 3C273 might have been one of many similar objects. But from our vantage point, separated by billions of years, it stands out as something extraordinary. Studying the central engine also helps explain how galaxies grow. Supermassive black holes gain mass as they consume material from their surroundings. Quasar phases are opportunities for rapid growth. As the black hole grows, it influences the structure of its host galaxy. The radiation from the quasar can push gas outward, affecting future star formation. This feedback mechanism shapes the evolution of galaxies over long periods. In this way, quasars are not just bright lights in the distance. They are active participants in the shaping of the universe. Their energy output affects the distribution of matter. Their jets can heat gas in surrounding regions. Their growth alters the gravitational environment. They are engines not only in a literal sense, but also in terms of cosmic influence. As more was learned about 3C273, the central engine became less mysterious. It remained extreme, but its structure could be understood through established physical principles. The key lay in observing the effects of the engine and working backward to determine the cause. Each observation added a piece to the puzzle. Over time, the picture became clear. Even now, with advanced telescopes and sophisticated simulations, the central engines of quasars continue to be areas of active research. There are still details to refine. There are still questions about how jets are launched, how disks behave near the event horizon, and how magnetic fields are structured. But the core model remains strong. The heart of a quasar is a black hole consuming matter through an accretion disk, powered by gravity and shaped by rotation. Thinking about this process while settling into a calm moment creates a contrast between the stillness of your surroundings and the intensity of the physics involved. Yet the contrast isn't jarring. Understanding the central engine doesn't create anxiety. It simply adds depth to the appreciation of how the universe works. The mechanisms might be extreme, but they are consistent and predictable once the underlying principles are known. As astronomers continued piecing together the structure of quasars and the processes surrounding them, their focus naturally shifted toward the central object responsible for all this activity. The accretion disk, the jets, the extreme radiation, and the rapid variability all pointed toward a single conclusion that became more difficult to ignore with each new observation. At the core of 3C273, and the core of every quasar, there had to be a supermassive black hole. Not just any black hole, but one so large and so dense that it could influence matter across enormous distances and convert that inflowing material into the extraordinary amount of energy emitted by the quasar. Understanding the nature of this central black hole required looking closely at the behavior of the surrounding gas. Since the black hole itself gives off no light, astronomers had to infer its properties indirectly, using the motions of matter near it. This approach is similar to watching debris circle a drain to estimate how strong the pull must be. The speed, temperature, and distribution of the gas provide clues about the mass and structure of the object drawing it inward. In the case of 3C273, the gas near the centre moves at remarkable speeds. The broadening of the spectral lines indicates that some of the material is orbiting the core at thousands of kilometers per second. Such velocities require a massive central object with a strong gravitational pull. No cluster of stars could produce that influence. A star would not be dense enough. Only a supermassive black hole could match the observations. Estimating the mass of the black hole involves measuring the velocities of the orbiting gas and determining the size of the region where the radiation is produced. These measurements lead to a mass estimate in the hundreds of millions of solar masses. This means the black hole at the centre of 3C273 contains the mass of several 100 million suns compressed into a region significantly smaller than our solar system. The scale is difficult to grasp in everyday terms, but the method of determining it is clear. The behaviour of the gas reveals the nature of the object controlling it. One might wonder how such a massive black hole forms in the first place. Black holes with a few times the mass of the Sun form from collapsed stars, but these stellar black holes are far smaller than the monsters found at the centres of quasars. Supermassive black holes likely grow through multiple pathways. They may begin as smaller black holes formed from the first generation of massive stars. They might merge with other black holes over long periods, and they definitely gain mass by consuming gas and dust pulled toward the galactic centre. During active phases, when the accretion disk forms, the black hole can grow rapidly as matter spirals inward. This growth is one of the features that makes quasars particularly interesting. They represent periods when black holes are gaining mass efficiently. The energy released during this process is a side effect of the matter heating as it falls into the gravitational well. While the black hole itself increases in size, the surrounding regions glow intensely. Observing quasars allows astronomers to witness black holes in the act of growing, something not easily seen in quieter galaxies. Another important aspect of supermassive black holes is their ability to influence the structure of their host galaxy. The energy output from a quasar can push gas outward, sometimes preventing stars from forming. This process, known as feedback, shapes the long-term evolution of galaxies. In the case of 3C273, the energy released by the quasar likely affected the distribution of gas in its host galaxy. Although the galaxy is difficult to observe directly because of the quasar's brightness, subtle features in the surrounding environment suggest that the intense radiation and jets have influenced the region. Understanding the behaviour of supermassive black holes also required considering the role of rotation. Black holes can spin, and the spin has significant consequences for the behaviour of the accretion disk and the jets. A rotating black hole drags space around it, a phenomenon predicted by general relativity. This effect allows magnetic fields near the black hole to twist, channeling energy outward through jets. The rotation also affects how efficiently the black hole converts in falling matter into radiation. Observing the jet of 3C273 hints that the black hole at its centre is spinning rapidly. The alignment, brightness, and structure of the jet match models where the black hole has a significant rotational speed. The presence of a well-defined jet suggests a stable orientation maintained over long periods. Jets require a consistent axis, and changes in orientation would produce different emission patterns. The stability of the jet indicates that the central black hole has been rotating steadily for a very long time. Another clue about the black hole's properties comes from the way the quasar emits energy across multiple wavelengths. Different parts of the accretion disk produce different types of radiation. The outer parts emit in optical and infrared wavelengths. The intermediate regions emit ultraviolet light. The inner regions, where the gas is hottest, emit X-rays. Observations of 3C273 across all these wavelengths provide a detailed map of the temperature distribution within the disk. This map helps astronomers determine how close the gas is orbiting to the event horizon, the point of no return around the black hole. The presence of X-ray emissions also reveals the structure of the corona, a region of energetic particles above the disk. Similar to the corona of the Sun but far more intense, this region influences the shape of the X-ray spectrum. The corona can scatter light from the disk, altering its energy. Understanding these interactions provides insight into the processes occurring at the very inner edge of the accretion disk. Despite the complexity of these models, the underlying principle is simple. The black hole doesn't produce light. The matter outside it does. The closer the matter gets to the black hole, the more energy it releases before crossing the event horizon. This energy creates the quasar's brilliance. The black hole acts as the engine, while the accretion disk and the jets serve as the visible and measurable components. One interesting feature of 3C273 is its relative brightness in optical light. Most quasars are so distant that they appear faint even in large telescopes, but 3C273 is bright enough to be seen with amateur equipment under good conditions. This brightness makes it more accessible for detailed study. It also means that the black hole must be producing a tremendous amount of energy. Even after travelling billions of light years, the light remains strong. This extreme luminosity leads to another question. How much matter must the black hole be consuming to maintain this brightness? Astronomers can estimate the accretion rate by comparing the observed luminosity to the theoretical efficiency of accretion. The calculations show that the black hole in 3C2273 consumes the equivalent of several Earth masses of material each year, sometimes more. This rate can fluctuate, causing variations in brightness. These variations provide additional information about the structure of the disk and the processes occurring near the event horizon. Understanding the feeding process also helps explain the long-term behavior of quasars. A black hole cannot remain in a highly active state indefinitely unless it has a continuous supply of fuel. In many galaxies, the central regions are not dense enough in gas to sustain long-term quasar activity. This is why most galaxies today, including the Milky Way, do not host quasars. Their black holes are still present but lack the supply of matter needed to form active accretion disks. The environment of 3C273, however, clearly contains enough gas to support prolonged activity. This supply might come from interactions with nearby galaxies, internal processes that funnel gas inward, or remnants of early galactic structure. Whatever the source, it creates conditions that allow the black hole to consume material continuously and maintain its luminosity. The structure of the accretion disk is another key component in understanding how the black hole feeds. The disk is not a smooth, uniform surface. It contains regions of turbulence, density fluctuations, and temperature gradients. These features affect how the gas moves inward and how energy is released. Observations of brightness changes in 3C273 reflect these fluctuations. When more gas reaches the inner regions, the quasar brightens. When the supply slows, the brightness decreases. These changes can occur on timescales ranging from hours to years. Because of this variability, long-term monitoring of 3C273 has provided valuable information about the stability of its feeding process. Astronomers have tracked its brightness over decades, building a detailed record of its behavior. This record shows patterns that help refine models of accretion. It also reveals unusual events that can indicate changes in the disk or the structure of the jet. The jets themselves offer another window into the behavior of the black hole. The jet of 3C273 has been observed in multiple wavelengths, allowing astronomers to trace its structure over long distances. Changes in the jet's brightness or shape can indicate fluctuations in the central engine. These variations often lag behind changes in the accretion disk because the particles in the jet need time to travel outward. By comparing the timing of variations in different regions, scientists can estimate the speeds of the particles and the structure of the magnetic fields. The jet's alignment also provides information about the black hole's stability. A steady jet suggests that the black hole's rotation axis has remained consistent over long periods. This stability is important because it influences how the black hole interacts with its environment. A stable axis means the jet affects the same regions of space repeatedly. shaping the surrounding medium. In contrast, a changing axis would spread the jet's effects over a wider area. The study of supermassive black holes gained additional support from observations of other galaxies. The centres of many galaxies show motions of stars and gas that can only be explained by the presence of massive, compact objects. The black hole at the centre of the Milky Way, although far less active than 3C273, provides a nearby example. Observations of stars orbiting the centre of our galaxy reveal a black hole with millions of solar masses. This strengthens the case that supermassive black holes are common features of galaxies, not rare exceptions. The discovery of these central black holes in multiple galaxies supports the idea that quasars represent a phase in the evolution of galaxies rather than unique anomalies. Almost every large galaxy likely contains a supermassive black hole. Whether that black hole becomes active depends on the availability of matter. When the conditions are right, the black hole transitions into an active phase, creating the structures and behaviours associated with quasars. In this context, 3C273 becomes not just a dramatic example, but an illustration of a broader phenomenon. It demonstrates what happens when a supermassive black hole has access to abundant fuel and the right conditions to form an accretion disk and jets. It shows how the black hole can grow, influence its environment, and produce observable effects across vast distances. Understanding the black hole that powers 3C273 also means understanding that this object is not static. It changes, it evolves, it consumes matter, grows larger, and alters its surroundings. The accretion disk may shift, the jets may fluctuate, the corona may reorganize. These changes occur over different timescales, some short and some long. The black hole itself, though it grows over time, remains the central feature driving all these processes. Thinking about this structure brings clarity to how such distant objects can be understood through careful study. The black hole, though invisible, leaves clear signatures in the light and radiation emitted by the surrounding material. These signatures allow astronomers to build a consistent model even from billions of light years away. The quasar becomes a window into a part of the universe that is too extreme to observe directly but understandable through its effects. As soon as astronomers understood that the centre of a quasar contained a supermassive black hole surrounded by a bright and energetic accretion disk, their attention turned to another feature that stood out just as strongly. Some quasars, including 3C273, emit long, narrow streams of particles that extend outward from their centres for enormous distances. These streams are called jets, and they are among the most striking structures associated with active galaxies. What makes them so remarkable is not only their size, but the way they maintain their shape across distances that dwarf entire galaxies. Studying the jets of 3C273 required careful work across multiple wavelengths. Jets are not visible in ordinary light the way stars or galaxies are. Instead, different parts of the jet emit radiation in radio, optical, ultraviolet, and even X-ray ranges. Each wavelength reveals a different layer of activity, and connecting them builds a complete picture. When scientists observed the jet of 3C273, they found a structure extending tens of thousands of light years. This distance is hard to appreciate in everyday terms, but the scale is enormous. A light year is the distance light travels in a year, and multiplying that by tens of thousands places the jet far beyond the boundaries of the galaxy surrounding the quasar. The first task in understanding the jet was determining what it was made of. Jets consist of particles, mainly electrons and protons or positrons, moving at speeds close to the speed of light. These particles emit radiation through a process called synchrotron emission. When charged particles spiral around magnetic field lines at high speeds, they produce radiation across a wide range of wavelengths. This process explains much of the emissions observed from 3C273's jet. The pattern of brightness, the polarization of the light, and the distribution of wavelengths all match the characteristics of synchrotron radiation. Because synchrotron emission depends on the energy of the particles and the strength of the magnetic fields, studying the jet reveals information about the conditions near the central engine. For example, sections of the jet that emit X-rays require extremely energetic particles. These particles must have been accelerated recently or maintained at high energies over long distances. Understanding how this happens required detailed observations and advanced models. The fact that the jet remains bright over such a long stretch indicates that the acceleration mechanism is both powerful and sustained. Another clue about the jet structure comes from its alignment. Jets typically form along the rotational axis of the black hole and accretion disk. The consistent direction of the jet in 3C273 suggests that the black hole's spin axis has been stable over long periods. This stability is important because it shapes how the jet interacts with its surroundings. A stable jet travels outward in a narrow path. A changing axis would cause the jet to sweep across different areas, producing a different pattern of emissions. The narrowness of the jet also tells astronomers something about the conditions near the black hole. Producing a collimated beam requires an organized magnetic field. These magnetic fields arise from the motion of the accretion disk and the rotation of the black hole. The exact process by which the jet forms is still an active area of research, but the leading models involve the twisting of magnetic field lines near the event horizon. These twisted fields channel some of the energy from the infalling matter into the jet, accelerating the particles outward. Even with these models, the scale of the jet remains challenging to explain fully. Maintaining the jet's shape over tens of thousands of light years requires stability in both the magnetic fields and the structure of the quasar. If conditions near the black hole were chaotic or shifting rapidly, the jet would show signs of fragmentation or irregularity. Instead, the jet of 3C273 appears smooth and continuous in many observations. This suggests a long-term balance between the activity of the black hole and the structure of the surrounding environment. Another fascinating aspect of the jet is its brightness. The jet of 3C273 is one of the few quasar jets visible in optical light. Most jets require radio observations to be detected clearly. The optical brightness of this jet allows astronomers to study it in greater detail, including the shapes of individual regions along its length. These regions often appear as knots, brighter areas that represent places where either the jet material has encountered resistance or where the magnetic fields have compressed the particles. These knots indicate points of interaction or acceleration. By studying their spacing and brightness, scientists can understand how energy moves along the jet. Some regions of the jet also show signs of changes over time. Although the structure of the jet is stable on large scales, small modifications occur as new material flows outward. These variations can reveal how quickly the jet responds to changes in the accretion disk. When the disk becomes more active, the jet may brighten. When the activity decreases, the brightness of the jet may fade. These connections link the behavior of the disk to the behavior of the jet, providing insight into how energy is transferred from the inner regions to the outer ones. Understanding the speed of the jet is another important part of the picture. The particles in the jet travel at relativistic speeds, meaning they move close to the speed of light. Determining the exact speed requires analysing how the jet appears from Earth. Relativistic effects cause the jet to appear brighter and shorter on one side than the other, depending on the angle at which we view it. For 3C273, the jet appears brighter on the side pointing slightly toward us, because the particles are moving almost directly in our direction. This effect, known as relativistic beaming, enhances the brightness of the jet and makes it easier to observe. Relativistic beaming also affects how motion within the jet appears. Some knots seem to move faster than light, a phenomenon called superluminal motion. This does not indicate that the particles violate physical laws. Instead, it results from the combination of their high speed and their orientation relative to our line of sight. The apparent faster-than-light movement occurs when the jet points almost directly toward us. This effect further confirms the high speed of the particles and the alignment of the jet. The jets of quasars also have significant effects on the surrounding space. As the jet travels outward, it interacts with the intergalactic medium. This interaction can heat the gas, spread magnetic fields, and even influence the formation of new structures. In some cases, the energy from the jet can trigger star formation in nearby regions. In others, it can suppress star formation by heating the gas and preventing it from cooling enough to collapse into stars. The jet becomes a tool for the black hole to shape its environment far beyond the core. The influence of the jet highlights the scale of the processes involved. A supermassive black hole located at the center of a galaxy can affect regions far outside the galaxy itself. The jet becomes a conduit for energy released by the accretion disk, carrying that energy across huge distances. This energy can modify the structure of the galaxy and the space around it. It demonstrates the reach of the central engine and the role it plays not only in its immediate vicinity, but also in the broader cosmic environment. One question that arises when studying the jet is how long it can remain active. Jets require a supply of material from the accretion disk. As long as the black hole continues to feed, the jet can persist. However, if the fuel supply decreases, the jet will fade. The structure of the jet in 3C273 suggests that it has been active for a long time. The length of the jet and the brightness of the knots indicate sustained activity. This consistency reflects the stable conditions near the black hole and the availability of gas in the central regions of the host galaxy. Another important aspect of the jet is the way it provides information about the black hole's spin. A spinning black hole creates more powerful jets than a non-spinning one. The connection between jet power and black hole rotation helps astronomers estimate the spin rate of the black hole. By studying the jet in 3C273, scientists infer that the black hole is spinning rapidly. This rapid rotation is consistent with the high energy output of the quasar and the structure of the accretion disk. The jet also reveals information about the magnetic fields near the black hole. Magnetic fields play a crucial role in accelerating the particles and maintaining the shape of the jet. Observations of polarization in the jet's light show that the magnetic fields are organized and strong. These fields help channel the particles and keep the jet collimated. Without strong magnetic fields, the jet would spread out and lose its structure. While jets are often studied for what they reveal about the black hole, they also raise questions about the nature of the intergalactic medium. As the jet travels through space, it interacts with the thin gas between galaxies. These interactions create shock waves and compress the gas, producing emissions that can be observed through radio telescopes. By studying these interactions, astronomers learn about the density, temperature, and composition of the intergalactic medium. The jet of 3C273 provides a unique opportunity to study these interactions because of its brightness and length. The emissions from the jet reveal details that help model the intergalactic environment. This information improves our understanding of how galaxies evolve and how matter spreads across cosmic structures. Another way the jet provides insight is through its apparent knots. These knots likely represent regions where the jet has encountered resistance, or where the magnetic fields have compressed the particles. The spacing of the knots may reflect periodic variations in the accretion disk. A more active disk could produce stronger bursts of energy, creating brighter knots. A quieter disk would produce less pronounced structures. By comparing the knots along the jet, astronomers can track how the central engine has changed over time. The structure of the jet also raises questions about the long-term fate of the particles within it. Some particles may remain trapped in the jet for thousands of light years before eventually losing energy and merging with the intergalactic medium. Others may collide with gas clouds or other structures. The path of the jet influences how far these particles travel and where they ultimately end up. This process spreads energy and matter across large regions of space. Understanding the jet of 3C273 required combining observations from multiple telescopes. Radio telescopes revealed the structure of the jet at long wavelengths. Optical telescopes showed the brighter regions in visible light. X-ray observatories provided information about the highest energy particles. By merging data from different instruments, astronomers created a complete picture of the jet's structure. This multi-wavelength approach allowed them to see the jet across its entire length and understand how it behaves from the center of the quasar to the outermost regions. The jet also plays a role in calibrating telescopes. Because of its brightness and structure, it serves as a test target for new instruments. Observing the jet allows astronomers to check the alignment and sensitivity of their equipment. This practical use helps improve future observations of other objects. As we move outward along the jet, the brightness gradually decreases, the particles lose energy, and the emissions fade. But even at great distances from the core, the jet remains detectable. This persistence shows how far the influence of the black hole extends. The jet carries energy across scales that challenge our usual sense of distance. Thinking about the jet in this way adds another dimension to the story of 3C273. The jet is not just an accessory to the central engine, it is a major component of the quasar's behaviour. It provides information about the black hole, the accretion disk, the magnetic fields, and the surrounding space. It shapes the environment of the host galaxy. It reveals patterns of energy flow that help explain how quasars influence their surroundings. Brightness becomes a more complicated idea once you look beyond everyday experience. The light from a lamp or a street light, the glow of the moon, even the shine of the sun follow familiar rules. They grow dimmer with distance, they spread out, and they're powered by processes we understand. But when astronomers began comparing the brightness of 3C273 to entire galaxies, it became clear that something about this object didn't behave in any familiar way. You could move it billions of light years away, and it would still appear bright enough for small telescopes to detect. That alone suggests an output of energy far beyond anything produced by stars. To make sense of this, astronomers needed to compare 3C273 not to local light sources but to large-scale cosmic structures. Typical galaxies produce light through billions of stars. Some have bursts of star formation, some contain bright clusters, but even the most luminous galaxies distribute that brightness across wide areas. When viewed from a distance, their light blends into a diffuse glow. Stars, even in large numbers, can only produce so much energy. Nothing about stellar processes could match the concentrated luminosity of a quasar. The first major clue about how 3C273 becomes so bright lies in understanding that its energy is not produced by nuclear fusion. Stars fuse hydrogen into helium, releasing energy through that process. This is an efficient mechanism for stars, but extremely inefficient compared to the gravitational forces operating around a supermassive black hole. Fusion converts less than 1% of mass into energy. Accretion onto a black hole can convert more than 10 times that amount, sometimes much more depending on spin and disk structure. This enormous efficiency advantage means that if the black hole has enough material falling into it, the light produced by the accretion disk can exceed the output of billions of stars. The light of 3C273 emerges from a disk of matter, heated to extreme temperatures by gravitational compression. As material spirals inward, friction and turbulence increase the temperature to levels where the gas emits radiation across nearly every part of the spectrum. The outer regions shine brightly in visible and infrared wavelengths. As the gas moves inward, the temperature rises, producing ultraviolet and X-ray emissions. This layering of radiation adds together to create the intense brightness observed from Earth. What makes 3C273 especially intense is the sheer amount of material available to feed the central engine. The accretion disk around the black hole is thick and dynamic, constantly drawing in fresh material from its surroundings. This inflow can come from disrupted gas clouds, remnants of smaller galaxies, or internal structures in the host galaxy that funnel matter inward. The supply is not limitless, but for now it is abundant enough to sustain high energy output. The rate at which material enters the disk determines how bright the quasar becomes. For 3C273, The inflow is high enough to maintain the extraordinary luminosity that outshines entire galaxies. Another factor contributing to its brightness is the structure of the disk itself. In some quasars, the disk may be partially obscured or irregular. Dust lanes or complex geometry can scatter or block some of the emitted light. But 3C273 appears to have a relatively clear line of sight. There is minimal obstruction between the central disk and our vantage point. This clarity allows more of the emitted radiation to reach Earth without being absorbed or scattered. Even if some regions are blocked by dust or gas, enough light escapes to make the quasar appear extremely bright. The orientation of the quasar also matters. In many active galaxies, the angle from which we observe the central engine affects how bright the object appears. If the accretion disk is edge-on, dust may obscure the view, dimming the light significantly. If the disk is more face-on, the view into the energetic regions becomes clearer. Observations of 3C273 suggest that we see it at a relatively favourable angle. Not perfectly face-on, but open enough that the brightest parts of the disk are visible. This orientation minimises losses from obscuration and allows the quasar's full luminosity to stand out. Another contributor is the presence of the jet. While most of the light from 3C273 comes from the accretion disk, part of its brightness is enhanced by beamed radiation from particles in the jet. These particles move close to the speed of light. Because they travel in a direction that is not far from our line of sight, relativistic effects intensify their emissions. This means the jet appears brighter than it would if viewed from the side. The combination of disk radiation and beamed jet emissions increases the overall brightness of the quasar. These factors alone create enough luminosity to rival entire galaxies, but the scale of the emission makes the contrast even more dramatic. Light from 3C273 travels across roughly 2 billion years before reaching Earth. Over those distances, light spreads out and dimming occurs. Even so, 3C273 remains visible as a relatively bright point. If placed at a more typical galactic distance, something like the distance of the Andromeda Galaxy, it would overwhelm the night sky. It would appear brighter than any star except the Sun. That comparison illustrates how extreme the output must be for it to remain bright at its actual distance. The temperature of the accretion disk also plays a major role. The disk of 3C273 reaches temperatures far higher than any star can achieve. Stars have temperature limits determined by the balance of fusion and gravity. An accretion disk is governed by different physics. As material spirals inward, it reaches velocities and energies far beyond stellar limits. The inner regions of the disk emit radiation so energetic that it exceeds ultraviolet light, entering the X-ray range. These emissions add significantly to the quasar's overall brightness. When astronomers measure the luminosity of 3C273, they find that it emits more than 1 trillion times the energy of the Sun. In practical terms, that number is impossible to relate to everyday experience, but comparing it to galaxies helps. A galaxy with 100 billion stars might emit 100 billion times the luminosity of the Sun. 1 trillion is 10 times more. That means the quasar produces more energy than 10 full-sized galaxies, and yet it fits within a region comparable to the size of our solar system. Another important factor is the efficiency with which the black hole spins. A rapidly spinning black hole increases the amount of energy available in the inner disk. Spin affects how close material can orbit before plunging into the event horizon. Faster spin allows matter to get closer, increasing the temperature and efficiency of radiation. The evidence suggests that the black hole in 3C273 is spinning quickly. Its jet structure, its brightness, and its radiation patterns all match models where spin contributes significantly to the luminosity. But luminosity doesn't only come from the disk. Surrounding the disk is a region of gas known as the broadline region. This gas is illuminated by the intense light from the disk. As it absorbs and re-emits radiation, it produces strong emission lines across the spectrum. These lines add to the overall brightness. The broadline region also reflects variations in the disk. When the disk brightens, the lines respond accordingly. When it dims, the lines weaken. This feedback adds another layer of complexity to the light from 3C273. Still farther from the disk is the dusty torus, a ring-like structure made of dust and gas. This torus absorbs some of the light from the disk and re-emits it in infrared wavelengths. Although this infrared emission is not the primary source of brightness, it adds to the total energy output. The torus also shapes how the quasar appears depending on the viewing angle. For 3C273, the torus appears not to block much of the central region, allowing a clear view into the inner parts. As astronomers studied the structure of 3C273 more closely, they discovered that the quasar's brightness also fluctuates. These fluctuations happen over days, months, and years. The changes are linked to variations in the accretion rate. When more material enters the inner disk, the brightness rises. When the flow decreases, the luminosity drops. These fluctuations reveal details about the feeding process and the stability of the disk. They also show that the quasar is not a static object. It is continuously evolving and responding to the environment around the black hole. The fact that 3C273 remains bright even when its output varies demonstrates how powerful the central engine truly is. Even during periods of lower activity, the brightness remains extraordinary. When the quasar returns to a higher feeding rate, the luminosity increases, reinforcing its status as one of the brightest quasars in the observable universe. Another detail that contributes to its extraordinary brightness is the environment of the host galaxy. Although the host galaxy is difficult to observe directly because of the quasar's overwhelming glow, subtle features indicate that it contains large reservoirs of gas. These reservoirs supply the accretion disk and sustain the quasar's long-term activity. The presence of gas within the galaxy may also result from past interactions or mergers with other galaxies. These interactions help funnel material toward the center, ensuring a steady supply for the black hole. Because the quasar has access to abundant fuel, and because the feeding process is efficient, the energy output becomes exceptionally large. This combination of factors — fuel supply, efficient accretion, clear orientation, relativistic jets, and high spin — creates a perfect environment for extreme brightness. The brightness of 3C273 is also important for cosmological studies. Quasars serve as reference points for measuring distances and mapping the structure of the universe. Their luminosity allows them to be seen across vast spans of space. 3C273, because of its brightness and relative proximity compared to other quasars, became one of the first objects used to measure cosmological distances accurately. The study of its redshift helped confirm models of the expanding universe. Observations of its behavior helped refine methods for estimating the size of the broadline region and the mass of the central black hole. In this way, the brightness of 3C273 is not just an interesting characteristic, it is a tool for scientific understanding. Its luminosity provides a window into processes happening at enormous distances and allows researchers to test theories of accretion, jet formation, and galaxy evolution. Another way to appreciate the brightness is to consider what the quasar would look like if placed closer to Earth. If 3C273 were located in a nearby galaxy, its light would overwhelm the sky. Even at a distance of several million light-years, it would outshine every star visible to the naked eye. The night sky would have an additional bright object rivaling the moon in visual impact. This comparison helps clarify the raw energy output of the quasar. Despite all of these details, the reason 3C273 outshines entire galaxies ultimately comes down to the efficiency of gravitational energy conversion. The region around a supermassive black hole converts matter into energy with far greater effectiveness than any other known process. As long as the black hole has access to material, the output can remain extremely high. And because 3C273 has conditions that support long-term feeding, the luminosity stays elevated over long periods. Thinking about the brightness of 3C273 creates an interesting contrast with the quiet moment you may be in right now. The quasar is distant, intense, and active, yet the light you receive from it is gentle, softened by time and distance. You're observing the result of processes occurring on unimaginable scales, but the experience is calm. This contrast does not diminish the power of the quasar. Instead, it provides a sense of perspective. Something so bright and energetic still becomes part of a quiet night of reflection once it crosses the vast space between galaxies. Before astronomers understood what 3C273 truly represented, they had no reason to assume it possessed any exceptional power. It appeared as a point of light, nothing more. Measuring its brightness seemed like a routine task, the kind of measurement that had been performed countless times before. Yet the journey from those early observations to the recognition of its extraordinary power required a series of steps that revealed how much the universe can hide behind something that appears simple at first glance. The process involved examining its light in ways that went beyond brightness alone, comparing its properties across wavelengths, and trying to reconcile those results with expectations that turned out to be too small for what 3C273 was actually doing. To measure the power of any distant object, astronomers start by determining its apparent brightness. This is the brightness seen from Earth, without any correction for distance. A nearby candle looks brighter than a distant one even if they emit the same amount of light. Therefore, apparent brightness alone doesn't tell you how much energy a distant object produces. You need to know how far away it is. Once the distance is established, you can calculate the intrinsic luminosity, the true amount of energy the object emits. Measuring the distance to 3C273 became the key step, but that step required understanding its redshift. Redshift occurs when light stretches to longer wavelengths as the universe expands. The farther away a galaxy or quasar is, the more its light is stretched. When astronomers observe the spectrum of an object and see known atomic lines shifted toward the red end, they can calculate how fast the object is receding due to expansion. That recession speed allows them to determine how far away the object is. In the case of 3C273, the spectral shift was far larger than expected for something that looked like a star. This raised questions because stars within our galaxy have very small shifts compared to distant objects. Once Martin Schmidt identified the shifted hydrogen lines in 3C273's spectrum, the redshift became clear. The amount of shift implied a distance of roughly 2 billion light-years. At that distance, any object appearing as bright as 3C273 had to be producing an astonishing amount of energy. The numerical value exceeded the luminosity of entire galaxies, something unheard of at the time. Many astronomers initially had difficulty accepting the result because it forced a reconsideration of the scale of cosmic energy production. The next step involved translating the redshift into actual distance. At the time, cosmology was still developing its methods for calculating distances based on the expansion of the universe. The Hubble constant, which relates recession speed to distance, was not as precisely known as it is today. Even so, the redshift of 3C273 was so large that reasonable variations in the Hubble constant made little difference to the conclusion. No matter how the numbers were adjusted, the quasar remained extremely far away. Its apparent brightness, combined with that distance, led to a luminosity far beyond anything manageable by ordinary processes. To confirm these results, astronomers measured the brightness of 3C273 more carefully. Observations were made across multiple wavelengths. The more wavelengths involved, the more accurate the estimate of total luminosity becomes. In visible light alone, 3C273 was exceptionally bright for its distance, but visible light only offered a fraction of the full picture. In radio wavelengths, the quasar was strong. In ultraviolet, it was stronger. In X-rays, it was stronger still. Summing the emissions across all wavelengths produced a number that exceeded expectations by such a large margin that it forced a rethinking of the mechanisms that could produce such energy. Another part of measuring its power came from studying how quickly the brightness changed. Changes in brightness place constraints on how large the emitting region can be. If an object's brightness varies significantly within a few days, the region responsible for that change must be small enough for light to travel across it within that time. This is because light cannot transfer information faster than its own speed. 3C 273 showed measurable variability over short periods, indicating that the region producing the light was compact. Yet this compact region produced more energy than galaxies that span hundreds of thousands of light years. This combination, compact size and enormous luminosity, made it impossible to explain the object using models based on stars. A star could vary in brightness, but a single star could never reach the luminosity observed. A cluster of stars too dense to resolve individually might vary slightly if one of them exploded, but this process would produce different spectral signatures. Supernovae produce brief outbursts, not sustained luminosity. None of the known stellar processes matched what 3C273 was doing. Because the quasar's brightness included contributions from multiple wavelengths, astronomers had to measure its total output by combining different observations made by different instruments. This process required careful calibration. Detectors in one wavelength range behave differently from those in another. Atmospheric effects influence visible light, while X-rays require specialized space-based instruments. Combining these measurements created a more accurate picture of the quasar's power. The result showed that its energy output exceeded that of 1 trillion suns. This number forced researchers to consider new models. If a star couldn't do it, and a cluster of stars couldn't do it, and an exploding star couldn't sustain it, then something else had to be responsible. This is when the idea of an accretion disk around a supermassive black hole became essential. The accretion process could produce energy at a rate high enough to match the observations. By comparing the measured luminosity to theoretical predictions of accretion efficiency, astronomers could estimate the mass of the black hole. This method produced values in the hundreds of millions of solar masses. While this estimate aligned with the observations, astronomers wanted further confirmation. They turned to the broad emission lines in the quasar's spectrum. The width of these lines indicated that gas was moving at high speeds near the central engine. These speeds allowed researchers to calculate the mass of the central object by applying the same principles used to determine mass from orbital motion. This independent method produced similar mass estimates, reinforcing the conclusion that the quasar was powered by a supermassive black hole. Another way to measure the power of 3C273 involved analysing the jet. The jet's brightness and length indicated that enormous amounts of energy were being channeled outward at nearly the speed of light. By measuring the jet's apparent motion over time, astronomers could estimate how fast the particles were moving. Some regions appeared to move faster than light, an illusion caused by relativistic effects. These superluminal motions indicated that the particles in the jet were travelling at speeds extremely close to the speed of light. The energy required to accelerate particles to those velocities confirmed the power of the central engine. Radio observations of the jet showed that the jet retained its structure across thousands of light years. Maintaining a coherent beam over such distances requires sustained input of energy from the central region. This again reinforced the idea that the black hole was consuming large amounts of matter and converting a significant fraction of that matter into energy. Measurements of the jet provided another way to estimate the total power output of the quasar, and the numbers aligned with the earlier calculations. Infrared observations provided additional details. The dust surrounding the central region absorbs some of the radiation from the accretion disk and re-emits it in the infrared. By measuring the infrared output, astronomers could estimate how much energy was being intercepted and reprocessed by the dust. This value added to the total luminosity, ensuring that no major component of the quasar's output was overlooked. The consistency of the measurements across wavelengths demonstrated that the quasar's brightness was not the result of a temporary outburst but a sustained process. Another method used to measure the power of 3C273 involved reverberation mapping. This technique examines time delays between variations in the central continuum source and the responses in the broad emission lines. When the inner region brightens, the broad line region responds after a delay corresponding to the distance between them. By measuring this delay, astronomers can map the structure of the quasar in terms of light travel time. This gives a measurement of the scale of the regions involved. With this scale, the luminosity of the central region becomes more precise. Reverberation mapping confirmed the size of the broad line region and supported the mass estimates of the central black hole. These techniques taken together built a picture that was impossible to ignore. Every method pointed toward the same conclusion. 3C273 emitted more energy than entire galaxies. The consistency across methods strengthened confidence in the results. The alignment of the numbers ruled out errors in measurement or interpretation. The quasar's power was not an illusion created by orientation. It was not a temporary flare. It was not an unusual type of star. It was a sustained, massive output produced by processes unique to active galactic nuclei. With the power measurement confirmed, astronomers next turned to understanding the origin of the material feeding the quasar. This involved examining the host galaxy, the environment around the quasar, and the possible interactions with other galaxies. Although difficult to observe because of the quasar's brightness, faint structures around 3C273 suggest a galaxy that has experienced interactions or mergers in its past. Such events can funnel gas toward the center, providing the fuel needed for a quasar phase. Understanding where the fuel came from helped confirm that the luminosity could be sustained over long periods. If the galaxy contained sufficient gas reservoirs, the accretion process could continue producing the energy observed. Observations of the host galaxy provided indirect clues about its history and structure. These clues helped confirm that the quasar's brightness was not an anomaly, but a natural result of the conditions in that galaxy. As the measurements became more precise, 3C273 became one of the standard candles for studying quasar physics. Its brightness, stability, and accessibility made it an ideal reference object. Other quasars could be compared to it to determine their luminosities and distances. By studying 3C273 first, astronomers gained a model for interpreting the behavior of other, more distant quasars. This model helped refine cosmological measurements and contributed to our understanding of the structure of the universe. The ability to measure its power so precisely revealed not only the mechanisms of quasars, but the broader context of galaxy evolution. Quasar phases likely occurred in many galaxies long ago. Today, most of these galaxies are quieter. Their black holes remain, but the fuel supply has diminished. Quasars like 3C273 show what galaxies looked like during their most active phases. Understanding its power also provided insight into the kinds of environments required to sustain quasar activity. Only galaxies with sufficient gas could produce the levels of luminosity observed. This explains why quasars are more common in the distant universe, where galaxies were younger and gas-rich. It also explains why nearby quasars are rare. Over time, galaxies consumed or stabilized their gas, reducing the likelihood of new quasar phases. Working out how far away 3C273 truly is required astronomers to think in ways that stretched well beyond the methods used for objects inside the Milky Way. Nothing about its appearance offered an obvious clue. It looked like a star, and stars in our galaxy follow familiar rules when it comes to distance. But the moment astronomers realized its spectral lines were shifted far from their expected positions, they had to consider a different kind of measurement. Redshift wasn't just a detail in the spectrum. It was the key to placing the quasar on the map of the universe, far beyond anything previously known. Redshift is tied directly to the expansion of the universe. When light travels through expanding space, the space itself stretches the light. This causes the wavelengths to increase. The more space expands during the light's journey, the more stretched the wavelengths become. Red light has longer wavelengths than blue light, so when wavelengths stretch, the light shifts toward the red end of the spectrum. This shift isn't caused by the object physically changing colour. It is caused by the expansion of the universe acting on the light during its long trip across cosmic distances. This effect provides a way to measure how far away something is. If you know the pattern of spectral lines an object should have, say from hydrogen or helium, you can compare where those lines appear in the spectrum to where they should be. The difference tells you the redshift. With the redshift, you can determine the object's recession speed, and with that speed you can infer distance. For nearby galaxies, this method is straightforward. For something as distant as 3C273, the numbers become much larger, but the method remains the same. When Schmidt identified the hydrogen-Balmer lines in the spectrum of 3C273 and realized how far they had shifted, the first reaction was disbelief. The shift was not small. It was large enough to imply that the object was billions of light years away, yet it still appeared bright enough to be seen through modest telescopes. This combination didn't fit any known phenomenon at the time. It forced astronomers to confront the reality that they were dealing with something far more powerful than anything previously observed. To confirm the redshift, other spectral lines were checked. The consistency across multiple lines strengthened confidence in the measurement. The shift was real, the distance was enormous, and the brightness at that distance was unprecedented. This realization marked a turning point. Quasars could not be local objects. They were part of the universe on the larger scales. Translating redshift into distance requires a series of steps that depend on cosmological parameters. The most important of these is the Hubble constant, which determines how fast the universe is expanding. Even though the value of the Hubble constant was less precise when 3C273 was first studied, the redshift was so large that small uncertainties didn't affect the overall conclusion. Whether the Hubble constant was at the high or low end of early estimates, the quasar still ended up billions of light years away. It was not a marginal result. It was overwhelming. Understanding that distance required thinking about light in a different way. The light reaching Earth from 3C273 began its journey long before humans existed. Long before Earth had complex life. Long before the continents took the shapes they have today. The universe was younger then. Galaxies were different. The cosmic web had not fully developed. The light we receive now is a snapshot of a much earlier epoch. Measuring redshift doesn't just give distance, it gives time, a look-back time measured in billions of years. This idea, looking back in time, becomes central to understanding quasars. When we observe 3C273, we see it as it was nearly 2 billion years ago. The quasar might still be active today, but we won't know for another 2 billion years. Every observation becomes a form of archaeology. The light is a record preserved by distance and expansion. The farther away an object is, the older the information we receive. Redshift therefore functions both as a ruler and a clock. The measurement of redshift also helps determine how the universe has expanded over time. By observing objects at different redshifts, astronomers can compare how recession speeds change with distance. This comparison reveals the history of cosmic expansion. High redshift objects show the universe as it was when it was younger and expanding at a different rate. 3C273 is not among the highest redshift quasars, but its redshift was high enough at the time of discovery to reshape thinking about the scale of the cosmos. After determining the distance, astronomers could calculate the luminosity. This required correcting the observed brightness for the effects of distance. Light spreads out as it travels, so a distant object appears dimmer than a nearby object with the same intrinsic power. By reversing this dimming mathematically, astronomers estimated how much energy the quasar must emit. For 3C273, the corrected luminosity was astonishing. It exceeded that of entire galaxies. Without redshift, this calculation would have been impossible. The apparent brightness alone misled early observers because distance was not known. Once the distance was accepted, the next step involved verifying that the measured brightness was stable enough to support the luminosity calculation. This involved multiple observations over time. The quasar varied, but the range of variation was consistent with an object whose core was extremely compact. These variations didn't undermine the distance measurement. They reinforced it. If anything, they made the picture sharper. The variations fit the model of an accretion disk around a supermassive black hole, a model already supported by the Luminosity. The next layer of understanding came from comparing 3C273 to other objects with similar redshifts. As astronomers catalogued more quasars, they noticed patterns. Objects with high redshifts tended to be brighter and more energetic. They appeared more frequently at great distances than nearby. This distribution suggested that quasars were more common in the early universe. This insight would not have been possible without redshift measurements. By placing quasars at earlier epochs in cosmic history, astronomers realized they represented an active phase in galaxy evolution, not a permanent type of object. The method used to determine the distance to 3C273 also helped refine cosmological models. Redshift distance relationships contributed to determining the age of the universe, the rate of expansion, and the large-scale structure of cosmic evolution. Quasars became tools for probing these questions. 3C273, being bright and accessible, played an important role in early measurements. It helped calibrate techniques that were later applied to more distant, fainter quasars. Another way redshift helped reveal the nature of 3C273 involved studying absorption lines in its spectrum. Sometimes the light from a quasar passes through clouds of gas on its way to Earth. These clouds absorb specific wavelengths, creating absorption lines. The positions of these lines reveal the redshifts of the intervening material. Each absorption line corresponds to a cloud at a different distance. This method allows astronomers to map the distribution of gas between galaxies and study the intergalactic medium. The light from 3C273 carries a record of these interactions. Its spectrum contains not only information about the quasar itself, but about everything the light encountered along its path. These absorption lines become important for understanding cosmic structure. They show how matter is distributed across large scales. They reveal the presence of gas clouds that are otherwise invisible. They help map the cosmic web, the network of filaments, clusters, and voids that forms the backbone of the universe. The redshift of each absorption line indicates how far away each cloud is. This allows astronomers to build a three-dimensional map of matter distribution using quasar light as a probe. Although 3C273 is not as distant as some other quasars used for these studies, its brightness makes it especially useful. The strong signal allows high-resolution spectra, revealing details that fainter quasars might not show as clearly. The combination of moderate redshift and high brightness creates a valuable tool for studying both the quasar and the universe it illuminates. Redshift also plays a role in understanding how the quasar's light is altered by the expansion of the universe. As wavelengths stretch, they lose energy. This effect is subtle, but over billions of years it becomes significant. The light we receive is not only dimmer because of distance, but also because the stretching reduces its energy. Calculating this effect helps refine the luminosity estimate. It also reveals how the expansion of the universe influences the energy of distant objects. The concept of look-back time becomes particularly important here. When we observe 3C273, we are seeing it as it was billions of years ago. The conditions that produced the light may no longer exist in the same form. The quasar could have dimmed. The black hole could have entered a quieter phase. The surrounding galaxy might have changed. But because light takes time to travel, we see the past. This isn't a metaphorical idea, it's literal. The distance and the speed of light guarantee it. This realization makes redshift a powerful tool for studying cosmic evolution. By observing objects at different redshifts, astronomers build a timeline of how galaxies, stars, and quasars change over billions of years. 3C273 occupies a specific point on that timeline, showing what quasars looked like at a particular stage in the universe's history. More distant quasars show earlier stages. Nearby active galaxies show later ones. The timeline becomes clearer when these objects are placed in order using redshift. Another aspect of understanding distance involves the curvature of space. The The universe is not a simple flat grid. Its geometry is shaped by matter and energy. When calculating distances based on redshift, astronomers must account for this curvature. The expansion of the universe is not uniform through time. Early on, matter dominated. Later, dark energy became more influential. These shifts affect how distance is calculated. Although this complexity was not fully understood when 3C273 was first measured, modern cosmology incorporates these factors. Redshift remains the foundation for determining distance, but the calculations are more refined now. Despite the complexity, the basic principle remains straightforward. The greater the redshift, the farther away the object. For 3C273, the redshift places it billions of light-years from Earth. The light we see began its journey when life on Earth was microscopic. The continents were not in their modern positions. The Earth's atmosphere was different. The sun was younger. Everything about that time is preserved in the light that arrives today. The idea that distance translates into time also helps frame the quasar's power in a new way. Because we see the quasar as it was billions of years ago, its brightness represents the universe's younger, more energetic period. Quasars were more common then because galaxies were rich in gas. The early universe had conditions suitable for feeding supermassive black holes. By studying quasars at different redshifts, astronomers trace the decline of quasar activity as the universe evolves. This connection between redshift and cosmic history means that 3C273 is not simply a bright object. It is a marker on the timeline of the universe. Its light reveals conditions at a specific stage in cosmic evolution. Other quasars reveal other stages. Together they show how galaxies grow, how black holes develop, and how the universe changes. Light leaving 3C273 began its journey long before anything familiar existed on Earth, and tracing that journey requires shifting attention away from the quasar itself and toward the vast space between galaxies. The moment these photons departed from the region around the accretion disk, they carried with them information about the state of the quasar at that exact time. Nothing about their path was predetermined. They simply moved forward at the speed of light, unaffected by the passage of time in the way physical objects experience it. Their story is not one of aging, but of distance, expansion, and interactions that occurred during the immense span between their origin and their arrival here. The trip began inside an environment far different from the calm of deep intergalactic space. Near the accretion disk, temperatures were extreme, magnetic fields were strong, and matter moved at enormous speeds. Photons created in those regions had to escape a dense and busy environment. Before leaving the immediate surroundings of the black hole, the light interacted with gas clouds, electrons, and dust. Each interaction shaped the energy and wavelength of the photons. Some were absorbed and re-emitted, some scattered. Only a fraction managed to travel outward without being redirected back toward the disk. The light that eventually reached Earth represents the portion that escaped the inner regions and headed outward into space. Once outside the core, the photons passed through the broader environment of the host galaxy. This galaxy existed during a period when gas was more abundant than in most galaxies today. Clouds of hydrogen, regions of ionized gas, and patches of dust surrounded the quasar. Through these regions, the photons passed with varying degrees of interaction. Some wavelengths were absorbed by gas clouds and re-emitted in different directions. Others continued undisturbed. The presence of specific absorption features in the quasar's spectrum reflects these early interactions. They mark the fingerprints of the material the light encountered on its way out of the host galaxy. After leaving the galaxy, the photons entered intergalactic space, a region that might seem empty but contains thin clouds of gas, traces of dust and streams of matter associated with the large-scale structure of the universe. Although these materials are extremely sparse, they are spread across enormous distances, meaning the photons encountered them again and again in small but cumulative ways. These interactions are visible in the spectrum as absorption lines corresponding to different redshifts. Each line indicates a cloud of gas located somewhere between 3C273 and Earth, with each cloud lying at a distinct distance and time. These absorption features form a record of the matter in the universe between 2 points separated by billions of years of cosmic history. The photons carry this record not because they deliberately store it, but because every interaction leaves a measurable imprint. The path of the light becomes a timeline. Each absorption line corresponds to a cloud that existed at a certain epoch. By identifying their redshifts, astronomers can place those clouds within the larger structure of the universe at different times. This makes quasar light a valuable tool for mapping how matter evolved over billions of years. As the photons continued their journey, they passed through regions shaped by the gravitational influence of galaxies, clusters, and cosmic filaments. Gravity bends light, even when the light passes at large distances from massive objects. This effect, known as gravitational lensing, can slightly alter the path of photons. In most cases, the bending is too small to notice, but the cumulative effect across vast distances contributes to subtle distortions in observed positions and brightness. Although 3C273 does not show strong lensing, the photons would not have travelled through a universe without encountering at least some gravitational influences from distant structures. The largest factor affecting the light was the expansion of the universe itself. As space expanded, the wavelengths of the photons stretched. This stretching reduced their energy and shifted them toward the red end of the spectrum. Over billions of years, the amount of stretching became substantial. The photons emitted in the ultraviolet range arrived on Earth as visible or near-infrared light. This transformation reflects the cumulative effect of cosmic expansion on every part of the light's journey. The redshift does not result from motion through space alone, but from the expansion of space carrying the photons along. During this long voyage, the light moves steadily forward, oblivious to the changes happening on Earth. When the photons were still relatively early in their path, Earth was in a completely different state. The planet did not have continents arranged in the shapes we recognize today. The surface lacked the diversity of life now present. Multicelled organisms had not evolved yet. The atmosphere, the oceans, and the climate were drastically different. None of these changes affected the photons. They continued moving across the universe at constant speed, unbothered by the transformations occurring on each planet they passed by or each galaxy they moved near. The path through intergalactic space was not straight in the sense we usually imagine. Because space itself curves around massive structures, the photons followed the geometry of space-time. Their path was the straightest possible route in that curved geometry, but not a straight line in the usual sense. This distinction matters because it shapes how astronomers calculate the distance the light travelled. The expansion of the universe and the curvature of space complicate the relationship between redshift and physical distance. Even though the quasar's light took roughly 2 billion years to reach Earth, the actual separation between Earth and 3C273 today is larger. The universe continued to expand during the entire journey. By the time the photons reached the outskirts of the Milky Way, they encountered the gas and dust that make up the halo of our galaxy. The halo is much less dense than the disk, but it still contains material that can scatter and absorb light. Some photons were absorbed by hydrogen atoms in the halo. Others passed through unaffected. The relative clarity of this region allowed most of the quasar's brightness to remain intact, but small adjustments to the spectrum occurred here as well. These adjustments are measurable and help astronomers understand the composition of the Milky Way's halo. Passing through the disk of the Milky Way brought the photons into regions with more dust and gas. Dust grains absorb some wavelengths more effectively than others. This effect, known as interstellar reddening, causes objects to appear slightly redder than they truly are. The amount of reddening depends on the path the light takes through the galaxy. For 3C273, the reddening is minimal compared to objects observed through denser regions of the Milky Way, but it still contributes a measurable change to the spectrum. This must be corrected when analysing the light to determine its true characteristics. After crossing the interstellar medium, the photons approach the solar system. Compared to the intergalactic medium, the solar system is dense, but relative to our scale, it is mostly empty space. The photons pass through the outskirts of the Oort cloud, an enormous but extremely sparse region filled with icy objects. None of these objects blocked the light. The chance of a photon hitting one of these ancient frozen bodies is so small that it can be ignored. The photons travelled inward through the solar system without interference. Closer to the Sun, the photons pass through the solar wind, a stream of charged particles constantly flowing outward. This wind does not absorb visible light in any significant way, but its presence can cause minor scattering. Even so, the photons continued their path without substantial alteration. The inner solar system provided a relatively clear corridor. Eventually the photons approached Earth's atmosphere. The atmosphere does absorb some wavelengths of light, particularly in the ultraviolet and infrared ranges. But visible wavelengths, including much of the light from 3C273 that reached us, can pass through the atmosphere with relative ease. When the photons entered the atmosphere, some scattered due to interactions with nitrogen and oxygen molecules. This scattering can slightly dim the light or shift its direction, but not enough to prevent detection. As the photons reached the surface, they entered telescopes designed to focus and measure them. Inside a telescope, mirrors or lenses guide the light toward detectors. These detectors convert the energy of the photons into electrical signals. This conversion marks the end of the photons' journey. After billions of years of uninterrupted travel, they give up their energy in a moment, becoming part of a measurement that reveals the state of the quasar long ago. What makes this journey remarkable is not just the distance involved, but the information preserved along the way. The photons carry details about the temperature, composition and structure of the quasar at the moment they were emitted. They also carry the imprint of each cloud of gas they passed through. They reveal how much the universe expanded while they were in transit. They show the distribution of matter across cosmic scales. All of this information can be extracted through careful analysis of the spectrum. This means the journey of the light is more than a long trip. It is a record of cosmic history. If the universe had expanded differently, the redshift would be different. If the intergalactic medium had a different structure, the absorption lines would change. If the quasar had been brighter or dimmer at the moment of emission, the apparent brightness now would reflect that. The light serves as a messenger across time, bringing with it a snapshot of a distant past. Another important aspect of the journey involves the fact that light travels at a finite speed. Because of this limit, there is always a difference between where an object appears to be and where it actually is. When we see 3C273, we see it as it was nearly 2 billion years ago. Its actual state today could be entirely different. The quasar might have faded or brightened, the jet might have changed shape, the accretion disk might have thinned, the host galaxy might have collided with another galaxy. None of those changes affect what we observe now. The image we receive is a preserved moment in cosmic history. This concept applies to all distant objects, but quasars emphasize it because the distances involved are so immense. When astronomers compare quasars at different redshifts, they're essentially studying different eras of the universe. Higher redshift quasars show what the universe looked like when it was younger. Lower redshift quasars show later stages. The light from each serves as a time capsule. In the case of 3C273, the light represents a time when the universe was roughly 2/3 its current age. Galaxies were more active, gas was more abundant, stars were forming at higher rates, black holes had more opportunities to feed. The quasar's brightness reflects these conditions. By studying its light, astronomers gain insight not only into the quasar but into the universe at that time. The story of the light also shows how interconnected everything is. A photon created near a black hole billions of years ago ends its journey inside a detector on Earth. Along the way, it interacts with matter shaped by stars, galaxies, and cosmic structures. It reflects the large-scale behaviour of the universe and the small-scale structure of gas clouds. It unites processes separated by vast distances and timescales. Thinking about this journey adds another layer of understanding to the quasar itself. The photons we observe today were created by processes happening in a region of extreme physics. They emerge from an environment shaped by gravity, motion and energy on a scale far beyond anything familiar on Earth. Yet they arrive as calm signals. They do not carry heat or pressure. They simply deliver information through their wavelengths and intensities. Looking at 3C273 is not only a way to understand what a single quasar is doing, but also a way to step backward into a period of cosmic history when the universe behaved differently from how it behaves today. Each photon that reaches Earth from this distant object carries information about the conditions across billions of years of development. Even though the quasar itself is not from the earliest era of the cosmos, it still functions as a marker of an earlier time. When astronomers examine it closely, they find clues about how galaxies grew, how black holes developed, and how the broader environment of the universe evolved. By linking these pieces together, 3C273 becomes more than an energetic source. It becomes evidence for what the universe once looked like, and how it transformed into its present state. The moment its light left the regions around the accretion disk, the universe was younger. Galaxies were not as settled as they are now. Star formation was happening at a faster pace. Interactions between galaxies were more common. The quasar activity that 3C273 represents reflects those conditions. Quasars are rare today, but billions of years ago they were common. That difference alone reveals something important about the early cosmos. It suggests that the young universe contained an abundant supply of gas that could be funneled toward the centres of galaxies. With more available fuel, more black holes could enter active phases. Studying 3C273 and comparing it to other quasars at similar redshifts helps researchers understand how frequently galaxies reach these energetic stages and what that frequency implies about the state of the universe. One of the clearest indicators of early cosmic conditions is the level of star formation. When 3C273 emitted the light we see today, galaxies were forming stars at higher rates. The universe contained more cold gas available for star formation. Black holes benefited from this environment because the same gas-driven star birth could be drawn inward toward galactic centres. In many early galaxies, those inflows formed the accretion disks needed to power quasars. Even though 3C273 is relatively close in cosmic terms compared to the most distant quasars, it still occupies a period when this elevated star formation rate played an important role in galaxy behaviour. The quasar's luminosity helps confirm that the early universe was more energetic. The amount of radiation produced by 3C273 is only possible in an environment rich in material. The host galaxy must have had access to large quantities of gas to sustain such an active state. This supports the broader picture of a universe still filled with matter that had not yet settled into long-term stable structures. When astronomers compare the brightness of quasars at different redshifts, they see a decline in quasar activity as the universe ages. This decline matches what theories of galaxy evolution predict. As galaxies consumed their gas through star formation and other processes, less material remained for feeding black holes. 3C273 emits light from a period before that decline progressed too far, making it a useful anchor point on the timeline. In addition to indicating abundant fuel, the quasar helps reveal how black holes grew over time. The mass of the black hole in 3C273 is enormous, suggesting that supermassive black holes were already well developed during that epoch. If these objects existed early in the universe, they must have grown quickly. The fact that 3C273's black hole is so massive within 2 billion years of emission time supports theories that black holes grew through rapid accretion and mergers during the universe's early stages. Without quasars like this, it would be difficult to confirm whether such rapid growth occurred. Another important clue comes from the structure of the quasar's spectrum. The broad emission lines indicate fast-moving gas near the central engine. These lines show that the environment around the black hole was turbulent and energetic. This turbulence reflects conditions common in younger galaxies, where gas flows were not yet stable. The quasar's broad emission lines are signatures of that era's chaotic processes, giving astronomers a way to understand the physical state of matter in early galactic cores. Comparing these lines to those in quasars at other redshifts helps researchers map how these environments changed as galaxies aged. Absorption features in the quasar spectrum contribute further information about the early universe. Each absorption line corresponds to a cloud of gas lying between Earth and the quasar. These clouds span a range of distances and times. By analysing them, astronomers can study the intergalactic medium across billions of years. The appearance of these lines indicates the presence of hydrogen and other elements in varying states of ionization. The distribution of these features reveals how matter was arranged and how it evolved. During the period when the light left 3C273, the intergalactic medium still contained regions of moderately dense gas. These regions are visible in the quasar's spectrum as small but distinct absorption lines. The composition of these clouds provides clues about the chemical evolution of the universe. Early in cosmic history, only hydrogen and helium were abundant. Over time, stars created heavier elements. When these stars died, they released those elements into space. The amount of metals in the gas clouds along the line of sight to 3C273 helps determine how much star formation had occurred by that era. By examining the strength of metal absorption lines, astronomers can estimate the level of enrichment. The spectrum of 3C273 shows moderate enrichment, consistent with a universe where several generations of stars had already formed and died, but where chemical evolution was still in progress. Another way 3C273 informs our understanding of early cosmic structure involves the large-scale distribution of matter. The photons from the quasar pass through filaments and voids, formed by gravity acting on dark matter and normal matter. The pattern of absorption lines provides a rough map of this structure. When many quasars are studied together, astronomers can trace how the cosmic web developed. Although 3C273 is only one data point, its brightness allows for a high-resolution spectrum, making it especially useful for detailed study. It contributes information about the density and temperature of gas in various regions, helping refine models of how the cosmic web evolved from early irregularities into the structure observed today. Observations of 3C273 also shed light on the relationship between galaxies and the intergalactic medium. The light carries signatures of photoionization, a process in which intense radiation alters the state of surrounding gas. The quasar's radiation can ionize hydrogen far beyond the boundaries of its host galaxy. This effect helps astronomers understand how early quasars influenced the space around them. During the early universe, quasar-driven ionization played an important role in shaping the temperatures and ionization levels of the intergalactic medium. The extent of the ionized regions around quasars like 3C273 provides information about when the universe transitioned from a neutral state to an ionized one. This transition, often called reionization, occurred earlier than the epoch represented by 3C273. But quasars like it still contribute to understanding how ionization levels changed afterward. By measuring the absorption and transmission of ultraviolet radiation in spectra from objects around similar redshifts, astronomers can determine how transparent the universe was at different times. 3C273's spectrum, though not from the reionization period itself, reveals a universe already mostly ionized, but still containing pockets of denser gas. The quasar also gives insight into the distribution of energy across the early cosmos. The amount of energy released by 3C273 reflects processes common in that period. Supermassive black holes converting gravitational energy into radiation contributed significant heat and ionization to the intergalactic medium. This input influenced how gas cooled and condensed into galaxies. By comparing the energy output of quasars to the amount of gas available, astronomers can estimate how efficiently black holes grew and how much they influenced their surroundings. 3C 273's extreme luminosity demonstrates that black holes played a significant role in regulating star formation in early galaxies. Another aspect of early universe behaviour seen through the quasar involves the movement of galaxies. The redshift not only tells distance but provides information about the expansion rate of the universe at that time. By placing 3C 273 at its redshift and comparing it to other objects at different redshifts, astronomers reconstruct how expansion changed over billions of years. This helps refine the timeline of cosmic acceleration and determine when dark energy began dominating the universe's expansion. Though 3C 273 does not sit at a distance extreme enough to probe the earliest expansion history, it sits at a useful point on the curve, reinforcing models of how the universe transitioned between different expansion regimes. The quasar's brightness makes it valuable for studying gravitational lensing effects, even though it is not strongly lensed by large foreground structures. Small distortions in its image can reveal the presence of faint but massive objects along the line of sight. These distortions allow astronomers to detect clumps of dark matter that might otherwise go unnoticed. By analysing the small shifts in position or brightness caused by weak lensing, researchers map the distribution of dark matter in the earlier universe. 3C 2273 contributes to this effort by providing a stable, bright light source against which distortions can be measured. The fact that quasars like 3C 273 were more common in the early universe also leads to insights about galaxy interactions. Collisions and mergers between galaxies were more frequent when the universe was younger. These interactions often funneled gas toward galactic centres, triggering quasar activity. The existence of 3C 273 suggests that its host galaxy either experienced such interactions or had internal dynamics that drove gas inward efficiently. Observing many quasars at similar redshifts confirms that this was not an isolated scenario. Instead, it was part of a broader trend in early cosmic development. As researchers studied more quasars like 3C 273, they built a timeline of black hole growth. By comparing the masses of black holes at different redshifts, astronomers learned that supermassive black holes grew rapidly during specific periods. The mass of the black hole in 3C 273 fits this pattern. It confirms that by 2 billion years ago, many black holes had already reached enormous sizes. Without quasars, this rapid growth would be harder to confirm because black holes in quiet galaxies are more difficult to measure. Quasars make supermassive black holes visible across vast distances. Another clue about the early universe comes from the quasar's jet. The jet reveals information about the magnetic fields and rotation rates of black holes at earlier times. The jet of 3C 273 shows that black holes were spinning rapidly, even in the universe's earlier stages. This spin affects how black holes accrete matter and how they release energy. By understanding these properties, astronomers learn how black holes and galaxies co-evolved. The jet also provides evidence about how black holes influence large-scale environments by injecting energy into surrounding space. The quasar also helps clarify how galaxies change from active phases to more stable ones. By comparing 3C 273 to nearby active galaxies that are less energetic, astronomers see how activity declines over time. The universe transitioned from a period of widespread quasar activity to one where black holes are mostly quiet. Studying objects at different redshifts reveals this shift. 3C 273 is part of that continuum, showing a stage when activity remained high, but had already decreased from the peak seen in earlier quasars. Considering all of these details together, 3C 273 becomes a lens through which the early universe can be viewed and understood. It is not the earliest quasar known, nor the most distant, but it sits at a point where its brightness and relative closeness allow for detailed study with instruments across the electromagnetic spectrum. This combination makes it invaluable for understanding the conditions that shaped galaxies, black holes, and the cosmic environment billions of years ago. There is a certain irony in the way some of the most energetic and violent events in the universe end up becoming some of the most relaxing things to learn about, even when the processes involve crushing gravity, intense radiation, high-speed jets, and vast structures shaped by forces far beyond anything Earth could withstand. The experience of observing them from such an enormous distance turns the intensity into something quietly fascinating. This contrast becomes especially noticeable with objects like 3C 273. The activity at its core is fierce, but the light that reaches us carries none of that urgency. It arrives softly, reduced to a steady glow that slips through telescopes without disturbing anything around us. The reason this calmness emerges comes down to distance. The scale separating Earth from 3C 273 turns enormous forces into gentle impressions. Even though the quasar is converting matter into energy at extreme efficiency, firing jets across intergalactic space, and interacting with regions around it in ways that reshape large portions of its host galaxy, those events unfold far enough away that they cannot influence Earth physically. The energy spreads out over billions of light years, dispersing so thoroughly that by the time it enters a detector on a telescope, the signal is faint. The faintness makes it manageable. Instead of overwhelming sensors or creating visible disturbances, it ends up being something that can be recorded as a subtle change in wavelength or brightness. What begins as a staggering torrent of energy becomes, by the time it reaches us, something delicate enough to study with precision instruments. This distance also adds a layer of time separation. The violent processes we observe today occurred nearly 2 billion years ago. Whatever is happening at 3C 273 in the present is something we won't witness for another 2 billion years. The detachment from the moment of emission creates a sense of safety. Nothing about the current behaviour of the quasar has any immediate consequences for us. Even if a dramatic shift happened in the quasar's core right now, the information about that shift would not reach Earth for a very long time. This built-in delay softens the psychological impact of learning about the extreme energies involved. We observe everything at remove, knowing the events belong to a past era. Another dimension of this calmness comes from the way objects like 3C 273 gain context as part of the universe's broader story. The quasar represents one example within a large category of active phenomena. As astronomers study it alongside others, patterns emerge. These patterns reveal that even the most dramatic events follow consistent rules. Jets behave according to physical laws. Accretion disks radiate in predictable ways. Black holes influence matter through known gravitational principles. The familiarity of these rules reduces the sense of chaos. Instead of being something unpredictable and alarming, the quasar becomes part of an orderly system governed by forces that can be explained and modelled. Understanding these rules also provides stability in the interpretation of the quasar's behaviour. Even though the processes are extreme, they do not violate expectations. The energy produced by the accretion disk matches theoretical predictions. The broad emission lines fit models of gas moving at high speeds near a massive black hole. The jet follows patterns seen in other quasars and radio galaxies. Each observation confirms that the universe behaves in ways consistent with the laws of physics. This consistency helps create a sense of reassurance. The quasar may be violent, but it is not chaotic in a way that defies explanation. Another aspect that contributes to the calmness is the way the information reaches us. The data typically takes the form of long exposures, faint spectral lines, and slow variations in brightness. There is no abruptness in the observation. A telescope records photons steadily over time. Instruments gather data gradually. Graphs and spectra emerge through careful processing. Even when the underlying phenomena involve rapid changes on cosmic scales, the experience of observing them is measured and methodical. This process creates an atmosphere of quiet concentration rather than urgency. The contrast between the violence of the quasar's core and the calmness of the observation also arises from scale. human experience operates on timescales measured in seconds, hours, and days. Quasar activity unfolds over millions of years. The pace of galaxy-sized events is slow relative to human perception. Even features that vary over days or weeks still feel distant, because the reasons behind those variations lie in processes occurring in an environment far removed from daily life. This mismatch in timescales makes the quasar's activity feel unhurried when interpreted through human observation. Another factor that shapes this sense of calm is the lack of direct sensory experience. We do not hear the jet. We do not feel the radiation. We do not witness the gas clouds spiraling inward or the intense heating of material in the inner accretion disk. Every detail is abstracted through instruments. The only signals we perceive are numbers, graphs, and images that represent light measured by detectors. Without sound, motion, or tactile cues, the violence becomes something that can be understood mentally without triggering the sensory responses associated with danger. Observing the quasar becomes an intellectual activity rather than a physical one. This does not mean the underlying events are gentle. The environment near the black hole is aggressive. Gas accelerates to extreme speeds. Magnetic fields twist in ways that shape and launch jets. Temperatures rise to millions of degrees. Radiation streams outward across wavelengths from radio to X-rays. The gravitational forces near the event horizon shape the motion of matter in ways that defy everyday experience. But because none of this interacts directly with us, our minds are free to explore the details without the instinctive reactions that accompany immediate danger. Another part of this calmness comes from the realization that human observation itself does not affect the quasar. No matter how many times we study it, measure it, or interpret its data, nothing about our actions changes what is happening 2 billion light-years away. This independence reinforces a quiet feeling of distance. Observers can study the quasar without worrying about influencing it. The quasar operates on its own terms, unaffected by the presence or absence of human attention. This detachment also enhances the feeling that the universe is operating on scales far beyond human concerns. Even extreme events in space do not alter the rhythm of life on Earth. The quasar's jets continue to stretch across intergalactic space. Its accretion disk continues to radiate with enormous power. Its surroundings continue to evolve according to gravitational forces and the flow of nearby gas. These processes unfold regardless of whether anyone observes them. This realization brings a sense of perspective. Compared to these long-term cosmic activities, daily concerns feel small, and that shift in perspective contributes to the calming effect. There is also something soothing about predictability in the data. When astronomers analyze the spectrum of 3C273, they see patterns that match known atomic signatures. Hydrogen lines appear where expected, shifted by redshift but recognizable. Emission from ionized gas follows characteristic shapes. The smoothness of these patterns can feel steady. The orderly nature of spectral lines brings clarity to the experience. Even when the processes behind the lines are violent, the measurable outcome is structured. Another reason the quasar feels calm to observe lies in the way it connects to the larger narrative of the universe. Learning about 3C273 is not just about understanding a single object. It is about understanding how galaxies evolved, how black holes grew, how energy shaped cosmic environments, and how matter distributed itself across vast distances. Seeing the quasar in this broader context creates a sense of continuity. The violence in its core becomes a part of a larger story with consistent rules. The predictability of that story helps soften the intensity of the processes involved. This sense of calm extends to the way the quasar's light integrates into the night sky. When viewed through a telescope, 3C273 appears as a point of light, similar to a star. Its jet is visible only through detailed imaging. Without that imaging, nothing about the object's appearance reveals the extreme activity taking place at its center. This simplicity of appearance contributes to the calmness. The quasar is not visually overwhelming. It is subtle, requiring careful observation to reveal its true nature. This subtlety creates a gentle experience for the observer, even though the information behind the light is anything but gentle. Understanding the quasar's impact on its surroundings also reveals a contrast between the scale of its influence and the tranquility of observing it. The radiation from the quasar can heat gas across large regions of its host galaxy. The jet can carve pathways into the intergalactic medium. Shock waves propagate through surrounding gas, altering temperatures and densities. These effects shape future star formation and influence how the galaxy evolves. Yet none of these effects reach Earth. They remain confined to regions far removed from human experience. The difference between the quasar's local influence and the distant perception creates another layer of calmness. There is also something steadying about the fact that 3C273 fits within known cosmic patterns. It is one example among thousands of quasars. It follows trends observed in quasar populations. Its brightness, redshift, and spectral features align with what models predict. Even though it is one of the brightest quasars, it is not an outlier that disrupts established theories. Its existence reinforces the reliability of our understanding of black hole growth and galaxy evolution. That reassurance contributes to the sense of calm. The quasar's light also provides a chance to engage with something immense without being overwhelmed by it. The numbers describing its behavior, its luminosity, its distance, its mass, are vast, but they can be approached gradually. Learning about the quasar can be done at a personal pace. The data does not arrive in a rush. Observations build slowly. Understanding develops over time. This pace suits the flow of calm reflection. The quasar becomes a subject that invites slow contemplation rather than demanding immediate comprehension. Another way the quasar supports a sense of calm is through its consistency. While it varies in brightness, the changes occur within predictable limits. The variations do not disrupt the overall behavior. Long-term monitoring reveals cycles and trends that match models of accretion. The regularity of these changes creates an impression of stability, even within the dynamic processes occurring at the core. The quasar does not flicker unpredictably. It follows a steady pattern shaped by physical laws. The light that reaches Earth also carries the quiet of space itself. Space does not have sound because sound requires a medium. Even violent events unfold silently. This silence carries through to the observation. The quasar's energy does not arrive with noise or vibration. It becomes part of an environment defined by calm reception rather than sensory overload. This silence contributes to the sense that the quasar, despite its intensity, can be experienced in a relaxed way. Another contributing factor is the way observation separates events from personal stakes. Nothing about the quasar's behavior affects the immediate physical environment of the observer. Learning about it is optional. The information is not tied to survival or daily responsibilities. It becomes an experience of curiosity rather than obligation. That freedom supports a relaxed state of mind. Lastly, the inability to influence the quasar or alter its course encourages a form of acceptance. Observers cannot change anything about the object. Its activity is outside human control. This realization fosters a kind of detachment that can feel peaceful. The quasar simply exists, doing what it does, following the laws of physics. That acceptance allows the mind to rest within the understanding rather than trying to solve or change the situation. All of these aspects together explain why observing something so powerful feels unexpectedly calm. It is the distance, the time scale, the detachment from sensory experience, the consistency of physical laws, and the perspective that comes from recognizing how small Earth is in comparison. The violence remains real, but its effects are softened by the vast separation. Rather than beginning with the quasar itself, it can be helpful to first think about how difficult it would be to understand the universe's large-scale structure if objects like 3C273 didn't exist. The cosmos is enormous, far too large to map by simply looking at nearby stars or even nearby galaxies. Most of what fills intergalactic space is faint, diffuse, and nearly invisible. If astronomers had to rely only on the light from ordinary galaxies, the map of the universe would be incomplete. Quasars, however, have a brightness that cuts through the darkness across vast distances. They act as distant lighthouses, illuminating not just themselves, but the matter between them and Earth. Without quasars, the large-scale cosmic web would be much harder to detect and interpret. One of the main reasons quasars help map the universe is their extreme luminosity. Because they outshine entire galaxies, their light can pass through enormous stretches of space and still remain measurable. As the light travels, it interacts with everything along the way: gas clouds, galaxy halos, filaments of intergalactic matter, and even the gravitational influence of massive galaxy clusters. These interactions leave small but identifiable signatures in the quasar spectrum. When astronomers analyse those signatures, they can reconstruct what the light encountered during its journey. This turns quasars into probes of the universe, not just bright points at impressive distances. The most informative part of this process involves absorption lines. When quasar light passes through a cloud of gas, atoms in the cloud absorb specific wavelengths. These absorbed wavelengths appear as dips in the quasar's spectrum. Because each cloud lies at a different distance, each one has a different redshift. By identifying the redshift of each absorption line, astronomers can determine where along the line of sight the cloud must be. This creates a series of markers spaced between Earth and the quasar, like signposts stretching across billions of light years. With enough quasars, these signposts begin to reveal the structure of the universe on the largest scales. This method becomes powerful when applied across large surveys. A single quasar reveals the structures along a narrow path, but when thousands of quasars are observed in different directions, the absorption patterns begin to form a three-dimensional map. This map shows clusters of galaxies, long filaments of gas, and large empty regions called voids. These features form what astronomers call the cosmic web. The cosmic web is not visible directly through images, but it becomes clear through the patterns imprinted on quasar spectra. Every quasar extends the reach of this map, helping to fill in the structure of the universe piece by piece. 3C273 played an early role in this work because of its brightness. It was one of the first objects where high-quality spectra revealed detailed absorption features. Its spectrum showed not only information about the quasar itself, but also about the gas in front of it. As instruments improved, astronomers were able to observe more distant quasars, some with much higher redshifts than 3C273, but its proximity and luminosity still make it one of the clearest examples to study when refining methods for mapping cosmic structure. The precision available for 3C273 sets a standard for interpreting similar data from fainter or more distant objects. The most famous feature revealed by quasars is the Lyman alpha forest. This name refers to a series of absorption lines caused by hydrogen clouds scattered throughout intergalactic space. When quasar light travels through these clouds, each cloud absorbs a slightly different wavelength depending on its redshift. The result is a forest of lines in the spectrum. Each line corresponds to a location in the universe where there is diffuse gas. Although the gas in these regions is incredibly thin, the accumulation of these clouds along the line of sight makes their effects measurable. By studying the distribution of these lines, astronomers uncover the structure of matter on scales too large to observe directly. The Lyman alpha forest reveals that matter in the universe is not evenly spread out. Instead, it forms patterns. There are regions with more gas, regions with less, and boundaries between them. These patterns correspond to the underlying distribution of dark matter. Dark matter itself does not absorb light, but it shapes the distribution of gas through gravity. Where dark matter forms dense regions, gas tends to accumulate. Where dark matter is sparse, gas is more diffuse. Because of this connection, quasar absorption lines indirectly trace the structure of dark matter. Mapping the Lyman alpha forest is therefore a way of mapping the invisible framework of the cosmos. Quasars also help measure how the universe expands. The redshift of each absorption line gives information about the expansion rate at the time the light passed through that region. By comparing absorption lines at different redshifts, astronomers can determine how the expansion changed over time. This reveals how the influence of dark energy evolved, how matter density changed, and how the universe transitioned from being dominated by matter to being dominated by dark energy. Quasars extend this information to great distances, providing a timeline that complements studies using galaxies and cosmic microwave background measurements. Another contribution quasars make is through the study of large-scale clustering. When absorption features in different quasar spectra line up at similar redshifts, it often indicates the presence of a large structure such as a galaxy cluster or a filament. By analysing these correlations, astronomers can estimate the size, mass, and distribution of these structures. Surveys like the Sloan Digital Sky Survey have used thousands of quasar spectra to map these correlations across huge volumes of space. The result is a detailed picture of how cosmic structures formed and evolved. 3C273, because of its brightness and accessibility, helped test methods used in these surveys. Quasars also help identify the boundaries of cosmic voids. A void is a region with very little matter compared to its surroundings. When quasar light passes through a void, the spectrum contains fewer absorption lines. When it passes near the edge of a void, the density of lines increases as it encounters more gas. By analysing these patterns, astronomers can map the shapes and sizes of voids. This information helps refine models of how matter spread out after the Big Bang and how gravity shaped the cosmic web. Another way quasars help map the universe is through gravitational lensing. When quasar light passes near a massive object, gravity bends the light. This bending can distort the quasar's appearance, magnify it, or create multiple images of the same quasar. By studying these distortions, astronomers can measure the mass of the lensing object, even if that object is made largely of dark matter. Lensing provides a way to map mass distribution that does not emit light. Some quasars are lensed by galaxy clusters, revealing how dark matter is spread within those clusters. Although 3C273 is not strongly lensed, observations of it help refine the techniques used to analyse lensing in other quasars. Quasars with measurable jets, like 3C273, offer another method. Even though jet directions vary, the shape of a jet and its brightness changes can reveal how matter is arranged in nearby regions. When the jet interacts with surrounding gas, it produces shock waves. These interactions can trace the density of gas around the quasar. Although this mapping is more localized than absorption-based methods, it contributes to the broader picture of how gas behaves within and around galaxies. Another area where quasars contribute to mapping the cosmos involves studying the chemical evolution of the universe. The absorption lines of metals, elements heavier than helium, show how enriched different regions of the universe became over time. Metal absorption lines reveal whether gas clouds have been enriched by previous generations of stars. This information helps map where star formation occurred, where supernovae spread their elements, and how galaxies influence their surroundings. The presence or absence of metals in absorption lines at various redshifts helps outline the flow of matter between galaxies and intergalactic space. Quasars also help trace reionization, the period when the first stars and quasars ionized the neutral hydrogen that filled the early universe. Although 3C273 is not from the reionization era, studies of more distant quasars use the same methods refined through objects like it. The presence or absence of Lyman alpha absorption at high redshifts reveals whether the intergalactic medium was transparent or opaque to ultraviolet light. By mapping this transition across many quasars, astronomers trace how reionization spread across the expanding cosmos. The clarity of quasar spectra makes all of this possible. Their brightness ensures strong signals, their extreme distances provide long sight lines, and their stability allows careful measurements. Quasars do not require ideal alignment or unusual conditions to be useful. Any quasar bright enough to produce a clean spectrum becomes a tool for mapping the universe. Because of this, they remain essential for studying the cosmos on the larger scales. 3C273's importance comes partly from being such a bright, accessible example. It served as a testing ground for spectroscopy methods that later became standard in large surveys. It demonstrated how quasar light interacts with intergalactic matter and how that interaction can be used to trace cosmic structure. As technology improved, astronomers were able to observe much fainter and more distant quasars, expanding the map further. But 3C273 remains a cornerstone because it showed what was possible long before large surveys existed. The ability of quasars to map the universe extends to understanding how galaxies evolve within the cosmic web. Galaxies tend to form along filaments where matter density is higher. Quasars reveal these filaments through absorption patterns. By mapping where galaxies appear relative to the absorption features, astronomers can study how galaxies grow and cluster within the web. They can see how environment influences star formation, how gas flows along filaments feed galaxies, and how clusters of galaxies form at the intersections of filaments. Quasars even help measure the temperature of intergalactic gas. The width of absorption lines reflects the temperature of the gas clouds. Hotter gas produces broader lines, cooler gas produces narrower ones. By analysing these widths across many quasars, astronomers map temperature variations on large scales. This information reveals how energy from galaxies, quasars, and cosmic structure formation heated the universe over time. It shows which regions experienced strong heating and which remained cooler. Another contribution quasars make is helping measure baryon acoustic oscillations, subtle ripples in the distribution of matter left over from the early universe. These ripples appear as preferred scales in the clustering of galaxies and gas clouds. By studying absorption patterns across many quasars, astronomers detect these ripples and use them to measure the universe's expansion history. This technique complements galaxy surveys and helps refine measurements of dark energy. Quasars also help identify faint galaxies. When quasar light passes through a galaxy too dim to detect directly, the absorption lines reveal its presence. This method uncovers galaxies that would otherwise be missed in imaging surveys. Mapping these faint galaxies helps complete the picture of how matter is distributed. It reveals dwarf galaxies, gas-rich systems, and other small objects that play important roles in the evolution of the cosmic web. The light from quasars even helps map magnetic fields in intergalactic space. When polarized light passes through regions with magnetic fields, its polarization changes slightly. By measuring these changes across many quasars, astronomers can infer the structure and strength of magnetic fields on cosmic scales. Although this mapping is still developing, quasars provide one of the few ways to study magnetism beyond galaxies. All these methods work together to transform quasars into tools for understanding the universe as a whole. They serve as distant beacons whose light reveals the distribution, motion, composition, and structure of matter across billions of years. Without them, the cosmic web would be far harder to visualize. The influence of dark matter would be more difficult to trace. The evolution of gas, galaxies, and intergalactic environments would be less clear. When someone finally pauses to consider what it means to look at a distant object like 3C273, the experience often shifts from being purely scientific to something more personal, even though it stays grounded in straightforward facts. The realization settles in that the light entering the telescope at this moment began travelling long before the world looked anything like it does now. It makes the observation feel less like a simple measurement, and more like a connection, stretched across time so large that everyday comparisons don't capture the scale. That recognition doesn't rely on metaphor. It comes from the plain statement that the photons reaching your eyes, or a detector, were released almost 2 billion years ago. They began their journey before familiar continents existed, before most life on Earth had formed structures more complex than microscopic cells, before mountains we now know had risen. That straightforward timeline is enough to turn a scientific act into a quiet pause for thought. The idea of witnessing ancient light isn't tied to emotion in a dramatic way. It's rooted in an appreciation for the distance involved. Watching something that existed so far back on the cosmic timeline brings a kind of stillness, because there is nothing you can do to change what the light carries. Everything it reveals is already finished. The photons reaching us cannot be altered by any present event. They carry information about conditions as they were, not as they are now. That distance creates a kind of quiet separation. You're not witnessing an event unfolding in real time. You're observing a record, and records do not change based on observation. Thinking about this makes the entire experience feel steady. The light that left 3C273 took a predictable path shaped by the expansion of the universe. It did not rush. It did not accelerate or slow down. It moved at a constant speed, crossing space that itself changed as it travelled. Everything about its journey reflects consistent rules. The speed of light remained the same. The stretching of wavelengths followed known laws of expansion, and the interactions with gas clouds and gravitational structures left signatures that can be interpreted. Knowing that the photons travelled under conditions defined by the same physics that govern local environments adds a sense of order to the moment of observation. That order supports the feeling of reflection. Another layer of this quiet reflection comes from realizing that there is no requirement for anything in the present day to match the state of the quasar when the light left it. The object could have changed dramatically. It could have dimmed or brightened. Its jet could have shifted. The host galaxy could have merged with another galaxy. All those possible changes remain unknown until the light reflecting them finally arrives. This gap between what is known and what is currently happening reinforces the idea that cosmic time follows its own pace, separate from human time. It creates a kind of mental space where observation becomes almost like reading an old document rather than watching a live stream. That distance encourages a calm approach. Even more grounding is the understanding that this calmness isn't created through exaggeration or poetic framing. It arises from the nature of cosmology itself. The vast distances prevent any direct involvement. The universe does not ask anything from the observer in return for the information it offers. There is no task to complete, no change to influence, no immediate consequence that follows from examining the light. Observing ancient light becomes an experience free of responsibility. It invites a slow pace because the information has been waiting for billions of years and can wait a few more moments while the mind takes it in. Another part of what makes witnessing ancient light meaningful is the awareness that every photon collected carries a full record of its environment at the moment of emission. A single detected photon is not a fragment of a larger message. It is a complete particle of information. Its wavelength, energy, and slight shifts all reflect conditions near the quasar's core. When instruments detect enough of these photons, the patterns reveal details that would otherwise remain hidden. From this perspective, each photon is something that persisted across an expanse of time so large it becomes hard to compress into everyday thinking. That persistence alone can lead to reflection. It did not decay. It did not scatter into nothing. It travelled until it reached a destination capable of interpreting it. These photons continue arriving steadily. There is no special moment that separates the first photon of the night from the last. The stream is ongoing, reflecting a process that has been happening long before humans existed. This continuity brings another layer of calmness. The universe does not deliver information in fits or bursts. It does not require specific conditions for the light to continue arriving. As long as the quasar is active and the path remains open, the photons will keep coming. This gradual nature aligns well with a quiet moment of reflection. The universe gives time for contemplation without demanding that it be done quickly. There is also something steadying in recognizing that observing ancient light is a form of looking at the past without sentimentality. Nothing about the experience depends on nostalgia or longing. The past being observed is so distant that it belongs to a universe with properties that only existed during that period. When the photons left 3C273, the fabric of the cosmos had different densities, different temperatures, and different compositions. The galaxies visible at that time were shaped by different environmental forces. This distant past is not tied to human memory. It is simply a stage in cosmic evolution. Reflecting on it becomes a way to understand time in a neutral way, without emotional associations. That neutrality contributes to the quietness of the moment. The fact that the universe offers these records so generously also supports the reflective quality. Every direction in the sky contains objects at different distances, meaning the night sky is a layered collection of times. Looking outward effectively means looking into multiple periods at once. Some stars show their light as it was a few hundred years ago. Some galaxies show themselves as they were millions of years ago. Quasars like 3C273 extend that range to billions. This layered structure gives a sense of depth to the universe. It transforms the act of looking through a telescope into something like reading multiple chapters of history simultaneously, except each chapter exists at a different scale of time. Because these timescales are so large and so stable, they support calm reflection rather than urgency. Another detail that adds to the reflective experience is how the quasar appears when viewed through a telescope. Despite being the brightest quasar visible from Earth, 3C273 still looks like a point of light to the eye. It is not dramatic in appearance. It does not show its jet or its host galaxy in ordinary views. The simplicity of that point of light can feel almost out of proportion with the depth of information it carries. That contrast encourages a thoughtful moment. Something so small in appearance contains so much information about large-scale cosmic behavior. Observers often respond to that contrast by slowing down and taking in the idea rather than rushing through it. This simplicity also removes distractions. There is no visually overwhelming structure that dominates the field of view. The power of the observation lies in what the data means rather than in how it looks. This aligns with the sleep-oriented mood you've built throughout the script. The viewer or listener does not have to imagine anything noisy or chaotic. They can picture a quiet point of light, knowing that behind it lies a long and detailed story shaped by the universe's grand processes. That knowledge can be taken in gently, without forcing a particular emotional direction. Another quiet aspect of witnessing ancient light involves acknowledging that these photons travelled independently of everything that happened on Earth during their journey. They crossed periods when Earth experienced ice ages, when ecosystems shifted, when continents drifted. Civilizations rose and fell long before the photons completed their path. That independence highlights the scale of cosmic processes compared to human timelines. Recognizing this difference often brings a feeling of perspective. It becomes easier to step out of the immediate concerns of the day when thinking about events measured on multi-billion-year scales. That perspective naturally supports a calmer state of mind. Even the process of interpreting the light encourages reflection. Gathering the photons, splitting them into a spectrum, identifying the lines, measuring the redshift, and reconstructing the path they travelled all require careful, steady analysis. Nothing about the work is rushed. Research unfolds over long periods. Multiple observations are combined. Results are reviewed and refined. This slow pace echoes the calmness that comes from thinking about ancient light itself. The scientific process becomes part of the reflective experience. It rewards patience. It matches the scale of the universe in a small but meaningful way. It's also worth noting that observing ancient light requires accepting unknowns. We know what the quasar looked like at the moment the light left it, but we do not know what it looks like today. There is no way to speed up the information. This acceptance of limits is unusual in everyday life, where information is often immediate. But in cosmology, limits are built into the structure of the universe. Accepting them becomes a natural part of the experience. This acceptance brings a sense of calm because it removes the expectation of control. The The universe sets the terms, and observation happens within those terms. There is no negotiation. There is only patience. Another meaningful part of witnessing ancient light involves considering how small Earth is in comparison with the distances involved. The planet is a tiny point in a galaxy that is itself one of billions. The quasar sits far beyond even the outer reaches of the local group of galaxies. Despite this enormous separation, photons released near a supermassive black hole still find their way here. That idea alone brings a sense of connection that does not require sentiment or metaphor. It expresses the simple truth that the universe is interconnected through the movement of light. That connection supports a reflective mood because it shows how even distant objects participate in the same physical laws that apply everywhere. There is also something steadying about recognizing that ancient light will continue to arrive long after the present moment. Even if observers were to stop looking, the photons would keep traveling. Their journey does not depend on human involvement. It continues because physics allows it. The independence of these processes can bring a quiet sense of comfort. The universe does not require attention to keep functioning. It continues regardless. Knowing this can ease the mind. The quiet reflection deepens when thinking about how much information is carried by such a simple point of light. The quasar's luminosity, its black hole mass, the structure of its accretion disk, the state of the intergalactic medium, the distribution of hydrogen clouds, the history of cosmic expansion, all of this can be inferred from careful measurements of the light. The depth of understanding comes not from the brightness alone, but from the patterns within the light. This encourages a form of contemplation that is patient and methodical rather than hurried. Each detail emerges through steady processing. Nothing about it is overwhelming. Observing ancient light also creates a connection to people who study the same object decades ago. 3C273 was first identified as a quasar in the early 1960s. Since then, generations of astronomers have examined it. Each group added new pieces of information. Each had access to better instruments than the last. The story of the quasar is therefore also a story of scientific progress. Witnessing ancient light becomes a way to participate in a long-term human effort to understand the universe. This sense of continuity adds another layer of reflection because it shows how knowledge accumulates steadily over time. Even the idea that the quasar could one day fade adds to the quiet mood. Quasars do not stay active forever. Eventually, the supply of gas feeding the black hole will decrease, the accretion disk will weaken, the jets will fade, the quasar will transition into a quieter phase. When that happens, no new photons of that brightness will be released, but the light that has already left will continue travelling for billions of years. Future observers, far removed from today's era, may still see 3C273 as it appears now. That continuation reinforces the sense that witnessing ancient light places you within a timeline that extends far beyond your own lifetime. As all of these thoughts settle, the experience of observing something like 3C273 becomes more than a scientific fact. It becomes a chance to take a moment and appreciate what it means to live in a universe that offers such long-reaching signals. The calmness comes from the scale, from the stability, from the acceptance of distance, and from the understanding that the universe keeps sending information without demanding anything in return. Observing ancient light becomes a steady, quiet moment in which the enormity of the universe becomes manageable, not through simplification, but through the recognition that the universe's timeline allows room for reflection at any pace.